Welcome back. Tonight, we settle in with the faint, ancient whisper of light that has been traveling toward us for nearly 14 billion years, the cosmic microwave background, that gentle afterglow of creation itself, now cooled to just a few degrees above absolute zero, filling every corner of the universe with its soft, uniform hum. We will trace its quiet journey across the vast emptiness of space, letting the stillness of deep time carry us toward rest. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the early 1960s, in the gentle rolling countryside of central New Jersey, there stood a rather unusual structure on a low-rise known as Crawford Hill. This structure belonged to Bell Telephone Laboratories, and it resembled nothing so much as an enormous horn, or perhaps a giant ear trumpet lying on its side, pointed toward the sky. The antenna measured some 20 feet in length, and it sat mounted on a rotating base that allowed it to sweep across different portions of the heavens, collecting the faint whispers of radio waves that drift perpetually through the cosmos. 2 young scientists had been assigned to work with this peculiar instrument, and their names were Penzias and Robert Wilson, and neither of them could have known, as they began their careful calibrations in 1964, that they were about to stumble upon one of the most profound discoveries in the history of human understanding, though stumble is perhaps the appropriate word, for the discovery would come to them not through theoretical insight or deliberate searching, but through the patient investigation of what they initially believed to be a malfunction, or perhaps bird droppings. The Holmdel horn antenna, as the structure was formerly known, had been built several years earlier for a specific and rather practical purpose, which was to detect radio signals bounced off the Echo balloon satellites that NASA had launched into orbit. These early communication experiments involved inflating enormous metallic spheres in space, more than 100 feet in diameter, and using them as passive reflectors to bounce radio transmissions from one point on Earth to another, a technique that seems rather quaint now but represented the cutting edge of telecommunications research at the time. The horn antenna had performed admirably in these experiments, but by the mid-1960s, the Echo program was winding down, and Bell Labs decided to repurpose the instrument for radio astronomy, assigning Penzias and Wilson to survey the radio emissions from our own galaxy, the Milky Way. Penzias had been born in Munich, Germany, in 1933, the same year that brought such darkness to that country, and his family had fled to America when he was a child, eventually settling in New York, where he grew up to study physics and develop a keen interest in the invisible light that fills the universe. Robert Wilson hailed from Houston, Texas, and had completed his doctoral work at the California Institute of Technology, where he had gained experience with radio telescopes and the delicate art of measuring extremely faint signals from space. The 2 men made a complementary pair, both meticulous in their methods, both patient in their approach, and both committed to understanding their instruments so thoroughly that they could trust every measurement it produced. Before they could begin their astronomical survey, however, Penzias and Wilson needed to calibrate the antenna with extreme precision, which meant identifying and eliminating every possible source of unwanted noise that might contaminate their observations. Radio astronomers speak of noise in a particular way, describing it in terms of temperature, because the random electromagnetic fluctuations produced by a warm object have the same statistical character as the static one hears in a radio receiver. When they pointed their horn antenna at the sky, away from any known sources of radio emission, they expected to measure a certain amount of noise arising from the antenna itself, from the atmosphere above them, and from the electronic equipment in their receiving system, and they calculated what this background level should be with great care. What they found, instead, was a persistent excess, a gentle hiss of radio energy that corresponded to a temperature of approximately 3.5 degrees above absolute zero, which is to say 3.5 Kelvin, and which simply would not go away no matter what they tried. This excess noise was not large in absolute terms, but it was significant enough to interfere with their planned observations, and more troublingly, they could not explain where it was coming from. They pointed the antenna in every direction, north and south, east and west, toward the plane of the Milky Way and away from it, and the noise remained constant, uniform, unchanging, as though it pervaded all of space equally. The two scientists spent many months attempting to identify the source of this mysterious static. They examined their electronic equipment for defects. They looked for interference from nearby radio stations or military installations. They checked for radiation leaking from New York City, which lay some 30 miles to the north. They considered whether the noise might be coming from the atmosphere, or from the ground surrounding their antenna, or from atomic bomb tests that had occurred in the upper atmosphere during the previous decade. None of these explanations proved satisfactory, and the gentle hiss continued, patient and imperturbable, as though it had always been there and always would be. Eventually, their attention turned to the antenna itself, and specifically to the large aluminum throat of the horn, where they discovered that pigeons had taken up residence. A pair of these birds had apparently decided that the Holmdel horn antenna made an excellent shelter, and they had been roosting inside it, leaving behind a coating of what Penzias and Wilson, in their scientific notes, referred to diplomatically as white dielectric material. This seemed a promising explanation, for any warm substance coating the antenna would produce thermal radiation that might account for the excess noise, and so the two scientists set about the task of removing both the pigeons and their deposits. The pigeons, however, proved remarkably persistent. Penzias and Wilson captured the birds and arranged for them to be transported to the Bell Labs facility in Whippany, New Jersey, some 40 miles away, hoping that the distance would discourage them from returning. The pigeons, apparently unmoved by this relocation, flew back to Crawford Hill within a matter of days, having demonstrated the impressive homing instinct for which their species is known. The scientists trapped them again, and again the birds returned, and finally, with some reluctance, Penzias and Wilson came to the conclusion that a more permanent solution was required, and the pigeons were shot. The antenna was thoroughly cleaned, the white dielectric material was scrubbed away, and when the measurements resumed, the mysterious noise remained exactly as it had been before, 3.5 degrees of unexplained static, coming from everywhere and nowhere at once. By the spring of 1965, Penzias and Wilson had largely exhausted their ideas for eliminating the noise, and they had begun to accept, with some frustration, that it might represent a genuine phenomenon rather than an instrumental artifact, though they had no notion of what that phenomenon might be. The discovery that would transform their nuisance into a Nobel Prize came about through a chance conversation, when Penzias happened to mention his difficulties to a colleague named Bernard Burke, an astronomer at the Massachusetts Institute of Technology. Burke recalled hearing about a theoretical prediction that intrigued him, and he suggested that Penzias telephone a physicist at Princeton University named Robert Dicke, who was working on something that might be relevant. What Penzias did not know, as he placed that telephone call, was that Robert Dicke and his colleagues at Princeton, located just 30 miles from Crawford Hill, had been preparing to search for precisely the signal that he and Wilson had accidentally found. The Princeton group, which included physicists named Jim Peebles, Peter Roll, and David Wilkinson, had been developing the theoretical framework and building the experimental apparatus to detect a faint background of microwave radiation that they believed should pervade the universe as a relic of its hot, dense origin. This radiation had been predicted decades earlier by other theorists, including George Gamow and his students Ralph Alpha and Robert Herman, but those predictions had been largely forgotten, and Dicke and Peebles had arrived at the same conclusion independently, working out the physics anew. When Penzias called, Dicke was sitting with his colleagues, eating lunch in his office, and after hearing the description of the Bell Labs measurements, he understood immediately what Penzias and Wilson had found. He put down the telephone, turned to the young physicists gathered around him, and said, quite simply, "Boys, we have been scooped." The race that Dicke had not even known he was running had ended before he could begin, and the cosmic background radiation that he had hoped to discover first had already been detected by two scientists who had stumbled upon it while trying to eliminate what they thought was noise. Dicke and his team drove to Crawford Hill shortly afterward to examine the Holmdel antenna and review the measurements, and they confirmed that Penzias and Wilson had indeed found what appeared to be the thermal afterglow of the Big Bang. 2 papers were prepared for publication in the Astrophysical Journal Letters, appearing side by side in the July 1965 issue. The first, written by Penzias and Wilson, described their observations in careful, understated language, reporting the detection of excess antenna temperature at 4080 MHz, without making any claims about its cosmological significance. The second paper, written by Dick, Peebles, Roll, and Wilkinson, provided the theoretical interpretation, explaining that the measured radiation was consistent with a universe that had begun in a hot, dense state and had been cooling ever since. It is worth pausing to appreciate the curious nature of this discovery, for neither Penzias nor Wilson had been searching for cosmological insights, and neither of them initially grasped the profound implications of what they had found. They were radio astronomers, skilled in the practical arts of antenna calibration and signal processing, and their expertise lay in measuring rather than theorizing. When they first detected the excess noise, they did not think of primordial fireballs or the origin of the cosmos. They thought of pigeons and atmospheric interference and faulty electronics. Their contribution was not the idea that such radiation should exist, which others had predicted, but rather the painstaking care with which they measured it, the thoroughness with which they ruled out alternative explanations, and the intellectual honesty with which they reported an observation they could not explain. This accidental quality of the discovery troubled some observers at the time, who felt that a finding of such importance ought to have arisen from deliberate theoretical motivation rather than serendipitous measurement. But science often works in unexpected ways, and the history of research is filled with discoveries that arrived unbidden, noticed by those who were looking for something else entirely. What mattered in the end was not how the measurement came to be made, but that it was made correctly, and that its significance was recognized by those equipped to understand it. In 1978, Arno Penzias and Robert Wilson received the Nobel Prize in Physics for their discovery of the cosmic microwave background radiation. The award recognized the importance of their observation, which had provided the strongest evidence yet that the universe had indeed begun in a hot, dense state, and which had transformed the Big Bang theory from a speculative hypothesis into a well-supported scientific framework. The Nobel citation made no mention of pigeons. The Holmdel horn antenna still stands on Crawford Hill today, preserved as a National Historic Landmark, its great aluminum throat pointed at the sky where it first detected the ancient light that fills all of space. The pigeons, one imagines, have found other places to roost, and the cosmic microwave background continues its patient hiss, undiminished by the years, carrying its message from the earliest epoch of the universe to anyone patient enough to listen. George Gamow was not the sort of physicist one might expect to predict the echo of creation itself, and perhaps that is part of why his remarkable insight was so easily misplaced by the scientific community, set aside like a note written on the back of a napkin and then forgotten in a coat pocket for nearly 2 decades. He was a large man, both in physical stature and in personality, standing well over 6 feet tall with a booming laugh and an irrepressible fondness for pranks, jokes, and what he called the lighter side of serious matters. His colleagues at various institutions over the years grew accustomed to finding rubber snakes in their desk drawers, to receiving letters written in elaborate codes, and to listening to Gamow hold forth on the deepest questions of cosmology while nursing a glass of vodka, which he consumed in quantities that would have incapacitated most other researchers. He was born Georgy Antonovich Gamow in the Ukrainian city of Odessa in 1904, and from his earliest years he displayed both a gift for physics and a temperament that refused to take solemnity too seriously, even when contemplating the origins of the universe itself. His path out of the Soviet Union is itself a story of remarkable determination and equally remarkable failure, the kind of biographical detail that seems almost too improbable for a physicist's life but which characterized Gamow's existence from beginning to end. In 1932, having already made significant contributions to quantum mechanics and nuclear physics, Gamow found himself increasingly constrained by Soviet authorities who were growing suspicious of scientists with international connections and cosmopolitan attitudes. He and his wife, Lyubov Vokmentseva, who was also a physicist and whom he called Ro, hatched a plan that seems in retrospect almost comically audacious, though at the time it was desperately serious. They would escape across the Black Sea by kayak, paddling some 170 miles from the Crimean Peninsula to Turkey, carrying with them only what supplies they could fit in the small boat along with their most essential possessions. The attempt, made in the summer of 1933, ended in failure, as such attempts so often do when the sea decides not to cooperate with human plans. A sudden storm arose and drove them back to the Soviet shore after they had paddled for some time into the darkness, exhausted and soaked and no closer to freedom than when they had set out. One might imagine that such a failure would have led to their immediate arrest and imprisonment in the growing network of labor camps that Stalin's regime was constructing across the Soviet landscape, but through some combination of luck and the chaos of bureaucracy, the Gamovs were not detained. Instead, Gamov managed to secure permission to attend a physics conference in Brussels later that year, the 1933 Solvay Conference, and once outside the Soviet Union, he simply never returned. He and Rowe made their way eventually to the United States, where Gamov would spend the rest of his career, first at George Washington University and later at the University of Colorado, always accompanied by his humor, his vodka, and his willingness to think about problems that more cautious physicists considered beyond the reach of serious investigation. It was at George Washington University, and later in collaboration with researchers at the Johns Hopkins Applied Physics Laboratory, that Gamov turned his attention to what he called the problem of the cosmic kitchen, the question of how the chemical elements that make up everything around us, from the iron in our blood to the oxygen we breathe to the carbon in every living thing, came to exist in the first place. By the late 1940s, Gamov had developed a picture of the early universe that was radically different from the prevailing view of a cosmos that had always existed in more or less its present form. He imagined instead a beginning, a moment of unimaginable density and temperature from which all matter and energy had expanded and cooled over billions of years. In this hot, compressed beginning, which a skeptic named Fred Hoyle would later mockingly call the Big Bang, a name that stuck despite being intended as an insult, Gamov saw the furnace in which the elements themselves had been forged. To work out the details of this primordial nucleosynthesis, as it came to be called, Gamov recruited a young doctoral student named Ralph Alpha, who had come to physics through night school and correspondence courses while working full-time at the Applied Physics Laboratory. Alpha was everything Gamov was not in temperament, meticulous and methodical and somewhat serious, but the two formed an effective partnership, with Gamov providing the grand vision and Alpha grinding through the calculations that such a vision required. Their work together culminated in a paper submitted in 1948 to the Physical Review, a paper that laid out the basic framework for understanding how hydrogen, helium, and trace amounts of other light elements could have been synthesized in the extreme conditions of the early universe. It was at this point that Gamov's love of jokes intruded upon the historical record in a way that has caused no small amount of consternation to historians of science ever since. The paper, as originally written, had two authors, Alpha and Gamov, but Gamov could not resist the pun that was staring him in the face. The Greek alphabet begins with alpha, beta, and gamma, and here was a paper by Alpha and Gamov, which sounded almost like alpha and gamma if one squinted at the names in the right way. All that was missing was a beta, and so Gamov, without asking permission and with complete disregard for the conventions of scientific authorship, added the name of Hans Bethe to the paper. Bethe was a distinguished nuclear physicist who had done important work on stellar nucleosynthesis, but he had contributed nothing whatsoever to this particular paper. Gamov simply could not resist the joke of having a paper on the origin of the elements authored by Alpha, Bethe, and Gamov, pronounced as Alpha, Beta, Gamma, and he found this so amusing that he went ahead and added Bethe's name to the manuscript before submission. The Alpha Beta Gamov paper, as it became known, was published on April 1, 1948, the date itself being another of Gamov's little jokes, and it attracted considerable attention both for its scientific content and for the curiosity of its authorship. Bethe himself took the prank in good humor, and there is some evidence that he even made minor contributions to the paper after his name had already been added, perhaps feeling that he ought to justify his inclusion in some small way. But for Ralph Alpha, who had done the bulk of the actual work and who was just beginning his scientific career, the joke was considerably less amusing. His doctoral thesis, the work of years of careful calculation, now appeared to the scientific community as the product of a collaboration with two established and famous physicists, one of whom had contributed the central ideas and the other of whom had contributed nothing at all except his convenient name. The prank would have consequences for Alpha's career and reputation that persisted for the rest of his life, though that bitterness was still in the future on that April Fool's Day in 1948. What followed the alpha-beta-gamma paper was in some ways more remarkable than the paper itself, though it received far less attention at the time and has often been overlooked in the standard histories of cosmology. Ralph Alpha continued working on the problem of the early universe, now in collaboration with another physicist at the Applied Physics Laboratory named Robert Herman. Together, Alpha and Herman pushed the calculations further than Gamow had taken them, working out in greater detail the physics of that primordial fireball and the processes by which it would have cooled and expanded over billions of years. And it was in the course of these calculations, later in 1948, that Alpha and Herman arrived at a prediction that was, in retrospect, one of the most important in the history of cosmology, though at the time it was largely ignored. If the universe had truly begun in a state of extreme heat and density, Alpha and Herman reasoned, then the radiation that filled that early cosmos, the intense glow of that primordial fireball, should still exist today. It would have been stretched and cooled by the expansion of the universe over billions of years, redshifted down from the visible light and beyond into the far infrared and then into the microwave portion of the electromagnetic spectrum, but it would still be there, filling all of space with a faint background glow. They calculated what the temperature of this remnant radiation should be, taking into account the expansion of the universe and the time that had elapsed since that hot beginning, and they arrived at a figure of approximately 5 degrees above absolute zero, 5 Kelvin in the temperature scale that physicists use for such calculations. The universe, if their theory was correct, should be filled with microwave radiation corresponding to a temperature of about 5 Kelvin, a prediction that could in principle be tested by anyone with sufficiently sensitive equipment pointed at the sky. Alpha and Herman published this prediction in a paper in the journal Nature, and they discussed it in subsequent publications over the following years, returning to the idea several times and refining their estimates. But the prediction never took hold in the way that one might expect for such a fundamental and testable consequence of the hot Big Bang theory. There were several reasons for this neglect, each of which contributed in its own way to the forgetting of what should have been an unforgettable prophecy. The journals in which Alpha and Herman published were not always the most prominent or widely read, the sort of places where a young physicist might place work that the more prestigious venues had declined. The technical details of their calculations were complex and involved assumptions about nuclear physics that not all cosmologists were equipped to evaluate. And there was the matter of Gamow's reputation, which had by this time become something of a liability for serious theoretical work. Gamow was, by the late 1940s and increasingly through the 1950s, better known to the general public than to his fellow physicists as a serious researcher. He had begun writing popular science books, beginning with his Mr. Tompkins series, which explained difficult concepts in physics through the device of a bank clerk who dreams himself into worlds where the speed of light is very slow or Planck's constant is very large. These books were charming and effective and brought the wonders of physics to a wide audience, but they also marked Gamow in the eyes of some colleagues as a popularizer rather than a true researcher, someone who had perhaps traded the rigor of scientific investigation for the easier pleasures of public acclaim. This was unfair to Gamow, who continued to do serious work throughout his career, but reputations in science are not always fair, and the association of the hot Big Bang theory with Gamow's increasingly playful public persona may have contributed to its being taken less seriously than it deserved. And so the prediction sat in the literature, largely unread and almost entirely unfollowed up, as the years passed and technology advanced and the means to test Alpha and Herman's prophecy became increasingly available. When Robert Dicke and his colleagues at Princeton began their own calculations about the remnant radiation from the early universe in the 1960s, they appear to have been entirely unaware that the same prediction had been made 17 years earlier and published in papers that were sitting in libraries no more than a few hours' drive away. The Princeton group reinvented the prediction independently, worked out the physics for themselves, and began building equipment to search for the radiation that Alpha and Herman had already told the world should be there. The irony of this situation, the duplication of effort and the missed opportunity for recognition, would only become apparent after Penzias and Wilson stumbled upon the cosmic microwave background in 1965, and the Princeton theorists realized that they had been scooped not only by the Bell Labs engineers but by a generation of physicists whose work had somehow slipped through the cracks of scientific memory. For Ralph Alpha and Robert Herman, The discovery of the cosmic microwave background brought not triumph but a complicated mixture of vindication and bitterness. Their prediction had been confirmed, spectacularly and precisely, but they had received almost no credit for making it. The Nobel Prize, when it was eventually awarded for work related to the cosmic microwave background, went to Penzias and Wilson for the discovery and later to others for subsequent measurements, but never to the theorists who had first predicted what should be found. Alpha and Hermann spent years writing letters, giving interviews, and publishing papers that documented their priority, trying to ensure that the historical record would reflect their contribution even if the official prizes did not. The bitterness never entirely faded, and one can hear it in interviews with Alpha from later in his life, the sense of having been cheated by the vagaries of scientific fame and the accidents of who reads which journals and remembers which predictions. George Gamow did not live to see this controversy fully unfold, nor did he live to receive whatever recognition might eventually have come his way. He died in 1968, just 3 years after Penzias and Wilson's discovery had confirmed the hot Big Bang theory that he had championed for 2 decades. His health had been declining for years, worn down by the vodka and the cigarettes and perhaps by the disappointments of a career that had promised more recognition than it ultimately delivered. He was 64 years old, which seems young now but which was perhaps not surprising given the life he had led. The universe he had imagined, hot and dense at its beginning and still glowing faintly with the afterlight of that primordial fire, had been proven real, but Gamow was gone before the implications of that proof could fully unfold, before the cosmic microwave background became the cornerstone of modern cosmology that it is today. He had escaped the Soviet Union, though not by kayak across the Black Sea, and he had glimpsed the beginning of all things, and he had made his colleagues laugh with his puns and his pranks, and then he was gone, leaving behind the Alpha Beta Gamma paper and the prediction that almost everyone had forgotten, and the universe itself, still expanding, still cooling, still whispering the story of its birth to anyone patient enough to listen. In the early 1970s, when the cosmic microwave background had been known to science for less than a decade, a small group of researchers at NASA began to imagine what might be possible if they could place a detector above the Earth's atmosphere, where the interference of water vapor and oxygen would no longer blur their measurements, where the quiet hum of the universe might be heard with unprecedented clarity. The proposal for what would eventually become the Cosmic Background Explorer satellite was submitted in 1974, just 9 years after Penzias and Wilson had first detected that faint primordial warmth with their horn antenna in New Jersey, and the scientists who drafted this proposal could not have known that 15 years would pass before their instrument would finally reach the darkness of space, nor could they have anticipated the particular sorrows and delays that would stretch between conception and launch. The original plan called for the satellite to be carried into orbit aboard the space shuttle, that remarkable and complicated spacecraft that NASA was developing throughout the late 1970s and early 1980s. And the Cosmic Background Explorer was designed with this launch method in mind, its dimensions and mass calculated to fit within the shuttle's cargo bay, its orbit selected to be achievable by the shuttle's trajectory from Vandenberg Air Force Base in California. The researchers waited as the shuttle program developed, as test flights were conducted, as the promise of routine access to space seemed to be approaching reality, and they refined their instruments and their plans with the patience that all large scientific endeavors require. And then, on the 28th of January, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, and 7 astronauts lost their lives in the cold Florida sky, and the entire American space program entered a period of grief and reassessment that would last for years. The shuttle fleet was grounded indefinitely while investigators sought to understand what had gone wrong, while engineers redesigned critical components, while the nation reconsidered the risks and costs of sending human beings into space. For the scientists who had been waiting to launch the Cosmic Background Explorer, this tragedy meant not only shared mourning but also profound uncertainty about whether their mission would ever fly at all. During the long months that followed the Challenger disaster, the team responsible for the Cosmic Background Explorer faced a difficult choice, and they chose to adapt rather than to wait. They redesigned their satellite to fit atop a Delta rocket, an unmanned expendable launch vehicle that had been carrying payloads into space reliably since the early 1960s. and this redesign required that they reduce the mass of their spacecraft and reconfigure its shape while preserving the essential capabilities of its 3 scientific instruments. The work was painstaking and the timeline uncertain, but the team persisted because they understood that the questions they hoped to answer had been waiting since the beginning of the universe, and a few more years of human patience seemed a small price to pay. The project scientist guiding this effort was a man named John Mather, a careful and methodical researcher who had been involved with the mission since its earliest planning stages, who had helped to design the instrument that would measure the spectrum of the cosmic microwave background with unprecedented precision. Mather understood that the success of the mission depended not only on brilliant ideas but also on countless small decisions made correctly, on cables and circuits and cooling systems all functioning together in the unforgiving environment of space, and he brought to this work a quiet determination that would sustain the project through all its difficulties. Working alongside Mather was George Smoot, a physicist from the Lawrence Berkeley National Laboratory who led the development of the differential microwave radiometer, one of the 3 instruments aboard the satellite. Smoot's instrument was designed to search for tiny variations in the temperature of the cosmic microwave background, differences so small that they had never been detected from the ground, ripples in the ancient light that might reveal how the smooth early universe had begun to develop the structures that would eventually become galaxies and clusters of galaxies. Both men had devoted years of their lives to this mission, and both would see their patience rewarded in ways they could scarcely have imagined. On the 18th of November, 1989, the Cosmic Background Explorer finally rose into the sky above Vandenberg Air Force Base, carried by a Delta rocket into a polar orbit some 900 kilometers above the Earth. The satellite weighed approximately 900 pounds and carried within it a supply of liquid helium coolant that would keep its instruments cold enough to detect the faint warmth of the cosmic microwave background without interference from the satellite's own heat. This liquid helium would slowly boil away over the following months, and the engineers knew from the start that the cooling system would last approximately 10 months before the helium was exhausted, which meant that the most sensitive measurements would need to be completed within that window. The satellite also carried a remarkable sunshield designed to keep its instruments perpetually shadowed from the warmth of the sun, and its orbit was arranged so that it would sweep around the Earth while the Earth swept around the sun, allowing the instruments to gradually survey the entire sky over the course of 6 months. Every part of the ancient light arriving from every direction would be sampled and measured, and from these measurements the scientists would construct a complete portrait of the cosmic microwave background as it appears from our particular location in the universe. The first results from the Cosmic Background Explorer were announced at a meeting of the American Astronomical Society in January of 1990, just 2 months after launch, and what the scientists revealed that day was so extraordinary, so perfectly aligned with theoretical predictions, that the assembled astronomers rose to their feet in spontaneous applause, a standing ovation rarely seen at scientific conferences, where decorum and measured skepticism are typically the order of the day. The data showed that the cosmic microwave background has the spectrum of a perfect blackbody, the precise mathematical curve that describes how heated objects radiate energy at different wavelengths, and the match between the theoretical curve and the observed data was so exact that when the measurements were displayed on a graph, the error bars were smaller than the thickness of the line representing the theory. This was a profound confirmation of the hot Big Bang model of the universe, because only a universe that had once been in complete thermal equilibrium, with matter and radiation thoroughly mixed and interacting freely, could produce a spectrum so flawlessly described by the blackbody curve. Any other origin for the cosmic microwave background would have left some irregularity, some deviation from the theoretical shape, and the Cosmic Background Explorer found no such deviation within the limits of its measurements. The universe had indeed begun in a state of almost unimaginable heat and density, and the light we detect today is the cooled remnant of that primordial furnace, stretched and reddened by the expansion of space but otherwise unchanged in its essential character. The theoretical physicist Stephen Hawking, when asked about the significance of this measurement, offered the assessment that it was the most important discovery of the century, if not of all time, a statement remarkable for its boldness and yet not unreasonable when one considers what was at stake. Here was direct evidence about the conditions of the early universe, a message written in light that had been traveling for more than 13 billion years, and the message confirmed that our mathematical models of cosmic history were fundamentally correct. The universe had a beginning, and we could measure properties of that beginning with precision. But the spectrum was only part of what the Cosmic Background Explorer had been designed to find, and the second great result required more time and more careful analysis. The differential microwave radiometer, the instrument led by George Smoot, was searching for variations in the temperature of the cosmic microwave background from one direction to another, tiny differences that theory predicted must exist but that had never been detected. These variations, if they existed, would be extraordinarily small, on the order of 1 part in 100,000, which meant that a region of sky with an average temperature of approximately 2.7 Kelvin might differ from another region by only 30 millionths of a degree. Detecting such minute differences required not only sensitive instruments but also painstaking removal of all other sources of variation, including the motion of the Earth through space and the faint emission from our own galaxy. After more than 2 years of observations and analysis, the team was ready to announce their findings, and in April of 1992, George Smoot presented evidence that the cosmic microwave background is indeed not perfectly uniform, that there are ripples in the ancient light, tiny variations in temperature that correspond to slight differences in the density of matter in the early universe. These density variations were the seeds from which all later structure would grow, the primordial fluctuations that gravity would amplify over billions of years into galaxies and clusters and the great cosmic web of matter that spans the observable universe. The detection of these anisotropies, as scientists call them, using a term that simply means variations with direction, was another moment of profound significance for cosmology, and George Smoot, in attempting to convey the importance of what they had found, offered a comparison that would prove controversial among some of his colleagues. He said that if you are religious, it is like looking at God, a statement that captured the sense of wonder and reverence that the discovery evoked, but that also blurred the boundary between scientific observation and spiritual interpretation in ways that made some scientists uncomfortable. Whether or not one found the comparison apt, there was no denying that the Cosmic Background Explorer had revealed something remarkable about the origins of structure in the universe. The liquid helium coolant that kept the most sensitive instrument operating at temperatures near absolute zero was exhausted after approximately 10 months, just as the engineers had predicted, and after that point the satellite continued to operate but with reduced capability. The mission had nonetheless achieved everything it had been designed to accomplish and more, providing data that would be analyzed and discussed for decades to come. The total cost of the Cosmic Background Explorer mission, from initial planning through launch and operation, was approximately $160 million, a sum that might seem large in everyday terms but that is modest by the standards of space science, representing perhaps 1/10,000th of what the United States spent on all government activities during the years the mission was under development. For this investment, humanity received confirmation of the hot Big Bang model, discovery of the primordial density fluctuations, and a new standard of precision for cosmological measurements. In 2006, 17 years after the launch and 14 years after the announcement of the anisotropies, John Mather and George Smoot were awarded the Nobel Prize in Physics for their work on the Cosmic Background Explorer. The Nobel Committee cited their discovery of the blackbody form and anisotropy of the cosmic microwave background radiation, recognizing that these measurements had transformed cosmology from a field of speculation into a field of precision science. Mather and Smoot shared the prize equally, honoring both the perfect spectrum and the tiny ripples, the smoothness and the structure, the unity and the variation that together characterize the oldest light in the universe. The Cosmic Background Explorer was only the beginning of a new era in cosmic microwave background research, and its measurements, remarkable as they were, would soon be surpassed by more sensitive instruments with finer angular resolution and broader frequency coverage. But it was the Cosmic Background Explorer that opened the door, that demonstrated what was possible, that showed humanity its first detailed glimpse of the universe as it appeared nearly 14 billion years ago, still glowing with the heat of its violent birth, already containing within itself the seeds of everything that would follow. The temperature of the cosmic microwave background, measured with extraordinary care by satellites orbiting high above our atmosphere, is 2.72548 Kelvin, give or take a mere 5700,000ths of a degree. This number, so precise and so carefully determined, represents one of the most accurate measurements in all of cosmology, and it tells us something quite remarkable about the nature of the universe we inhabit. 2.725 Kelvin is very cold indeed, just a few degrees above the absolute zero of temperature where all molecular motion would cease, and yet this faint warmth fills every corner of space, permeating the vast emptiness between galaxies, surrounding every star and planet, passing through you and through me at this very moment as we rest here together in the quiet of the evening. To understand what this temperature truly means, and why it matters so very much to the scientists who study the early universe, we must first consider the nature of blackbody radiation, a concept that emerged from the careful work of physicists in the late 19th and early 20th centuries. A blackbody, in the language of physics, is an idealized object that absorbs all radiation falling upon it, reflecting nothing at all, and that emits radiation in a very particular pattern that depends only on its temperature. The color and intensity of light from a blackbody follow a precise mathematical curve, and this curve tells us everything we need to know about how hot the object is, regardless of what the object is made from or how it came to be. The story of blackbody radiation begins in earnest with the work of German physicist Max Planck, who in the year 1900 made a discovery that would eventually revolutionize all of physics, though at the time it seemed merely a clever mathematical trick to explain an annoying discrepancy in the data. Physicists of that era had been struggling to explain the full spectrum of light emitted by hot objects, for the classical theories of the time predicted that such objects should emit infinite amounts of energy at short wavelengths, a clearly impossible result that became known as the ultraviolet catastrophe. Planck found that he could reproduce the observed spectrum perfectly if he assumed that energy could only be emitted or absorbed in tiny discrete packets, which he called quanta, with each packet carrying an amount of energy proportional to the frequency of the light. This assumption, made somewhat reluctantly by Planck himself, planted the seed that would grow into quantum mechanics, and it gave us the mathematical tools to understand precisely how temperature relates to the spectrum of radiation that a hot object produces. The blackbody spectrum that Planck derived has a characteristic shape, rising smoothly from zero at long wavelengths, reaching a peak at some intermediate wavelength that depends on the temperature, and then falling away again at shorter wavelengths. Hot objects peak at short wavelengths, which is why the filament of an incandescent bulb glows with visible light, while cooler objects peak at longer wavelengths, which is why warm bodies like our own emit most of their radiation in the infrared where our eyes cannot see. For an object at the temperature of the cosmic microwave background, this peak falls at a wavelength of approximately 1.9 millimeters, placing it firmly in the microwave portion of the electromagnetic spectrum, and this is of course why we call it the microwave background rather than, say, the infrared background or the radio background. The relationship between temperature and peak wavelength was first described mathematically by Wilhelm Wien, a German physicist who in 1893 formulated what is now known as Wien's displacement law. This law states that the wavelength at which a blackbody emits most strongly is inversely proportional to its temperature, so that hotter objects peak at shorter wavelengths and cooler objects peak at longer ones. The constant of proportionality in Wien's law has been measured with great precision, and when we apply it to the observed peak wavelength of the cosmic microwave background, we arrive at that same temperature of approximately 2.725 Kelvin. Wien's law thus provides an independent check on our temperature measurements, confirming that the radiation we observe from the early universe behaves exactly as blackbody radiation should. What makes the cosmic microwave background so remarkable and so useful for cosmological studies is that it is not merely a good approximation to blackbody radiation, but rather the most perfect blackbody ever observed in nature. When scientists measure the spectrum of the cosmic microwave background across a wide range of wavelengths, plotting the intensity of radiation at each frequency, the resulting curve matches the theoretical Planck blackbody spectrum to an accuracy that is quite simply unprecedented. The measurements made by the far-infrared absolute spectrophotometer aboard the COBE satellite in the early 1990s showed deviations from a perfect blackbody of no more than 50 parts per million, and subsequent observations have only confirmed this extraordinary agreement. No laboratory on Earth has ever produced a blackbody this perfect, for even the most carefully constructed experimental apparatus inevitably has small imperfections, tiny variations in temperature across its surface, minute reflections, and absorptions that cause departures from the ideal. The reason the cosmic microwave background achieved such perfection is that it had hundreds of thousands of years to reach thermal equilibrium in the dense plasma of the early universe, with photons and matter constantly exchanging energy through countless interactions, smoothing out any irregularities and producing a radiation field that was as uniform and thermalized as any physical system could possibly be. When this radiation was released as the universe cooled and became transparent, it preserved this perfect blackbody character, and the subsequent expansion of the universe cooled the radiation uniformly without disturbing its spectral shape, so that what we observe today is essentially a cooled but otherwise unaltered snapshot of that primordial equilibrium. This cooling from the early universe to the present day follows a simple and elegant relationship that tells us much about the history of cosmic expansion. When the cosmic microwave background was first released, approximately 380,000 years after the beginning, the universe had a temperature of roughly 3,000 Kelvin, hot enough that hydrogen atoms were just becoming stable for the first time. The radiation at that moment was not in the microwave range at all, but rather in the visible and near-infrared, with a peak wavelength comparable to the red light we see with our eyes. As the universe expanded over the following 13.8 billion years, the wavelengths of all those primordial photons were stretched along with space itself, a phenomenon known as cosmological redshift, and this stretching cooled the radiation according to a precise inverse relationship with the scale factor of the universe. The ratio between the temperature then and the temperature now tells us directly how much the universe has expanded since that time. Dividing 3000 Kelvin by 2.725 Kelvin gives us a factor of roughly 1100, which means that the universe today is about 1100 times larger in every linear dimension than it was when the cosmic microwave background was released. This remarkable number connects the temperature we measure with our microwave detectors to the grand sweep of cosmic history, allowing us to trace the expansion of space from a time when galaxies did not yet exist to the vast and ancient cosmos we inhabit today. The photons of the cosmic microwave background are astonishingly numerous, far more abundant than one might expect from such faint and gentle radiation. At the current temperature of 2.725 Kelvin, there are approximately 411 photons in every cubic centimeter of space, which may not sound like very many until one considers the sheer volume of the universe and compares this number to the density of ordinary matter. For every atom of hydrogen, helium, or any other element in the cosmos, there are roughly 2 billion cosmic microwave background photons, a ratio that has remained constant since the first moments after the beginning, and that provides important constraints on the physics of the very early universe. These photons are everywhere, passing through the walls of our homes, through the atmosphere of our planet, through the spaces between the stars, filling even the most remote voids between galaxy clusters with their gentle presence. The energy carried by each individual photon is exceedingly small, corresponding to microwave radiation with wavelengths measured in millimeters. And this is why the cosmic microwave background has no noticeable effect on our daily lives despite the hundreds of photons passing through each cubic centimeter of our surroundings every moment. The total energy density of the cosmic microwave background is approximately 420 microjoules per cubic meter, a tiny amount compared to the energy in starlight or in the ordinary matter of planets and people, and yet when integrated over the entirety of the observable universe, this adds up to a truly vast quantity of energy, a remnant of the hot dense state that preceded the formation of all the structures we see around us. Looking far into the future, we can trace the continuing cooling of the cosmic microwave background as the universe continues its expansion. If the current understanding of dark energy and cosmic acceleration is correct, the universe will expand forever, with the scale factor growing without limit as the eons pass. The temperature of the cosmic microwave background will continue to decline, dropping below 2 Kelvin, then below 1 Kelvin, asymptotically approaching but never quite reaching absolute zero. In the far distant future, trillions of years from now, the cosmic microwave background will have cooled to temperatures so low that its photons will have wavelengths measured in meters rather than millimeters, stretched into the radio portion of the spectrum by the relentless expansion of space. This ultimate fate, sometimes called the heat death of the universe, represents a state of maximum entropy in which all temperature differences have been smoothed away and no useful work can be extracted from any physical system. The cosmic microwave background, that perfect blackbody radiation that tells us so much about the youth of the cosmos, will by then have spread its energy so thin that it can barely be distinguished from the absolute zero of empty space. The temperature will approach a final value determined by the properties of dark energy and the geometry of an exponentially expanding universe, a value so close to zero that the distinction between something and nothing becomes almost meaningless. But that distant fate lies unimaginably far ahead, trillions upon trillions of years beyond any span of time that human minds can meaningfully comprehend, and for now the cosmic microwave background remains a warm and constant companion, filling the universe with its gentle glow of 2.725 Kelvin. Every measurement of this temperature, every careful observation of its spectrum, confirms the same remarkable story, that we live in a universe that was once hot and dense, that has been expanding and cooling for nearly 14 billion years, and that carries within it the faded afterglow of its own fiery birth. The numbers are precise, the physics is well understood, and the blackbody curve fits as perfectly as any theoretical prediction in all of science, a quiet testament to the power of careful observation and the deep regularities that govern the behavior of light and matter across the breadth of cosmic time. Let us turn our attention now to a moment in the early history of the universe that changed everything about how light moved through space, a transition so fundamental that it determines the oldest thing we can ever see with our telescopes, no matter how sensitive we make them, no matter how patient we become in our observations. This moment occurred approximately 380,000 years after the Big Bang, which sounds like an enormously long time when measured against a human life, but is really just the briefest flicker when set against the 13.8 billion years that have passed since then. If the entire history of the universe were compressed into a single calendar year, this moment would have occurred in the first few hours of January the 1st, somewhere in the quiet darkness before dawn on that metaphorical New Year's Day. Before we explore what happened at this time, it helps to understand what the universe was like in those first hundreds of thousands of years, that long stretch of time when everything was filled with a hot, dense substance that behaved rather differently from anything we encounter in our everyday experience. The universe was filled with plasma, which is a state of matter in which the temperature is so high that electrons cannot remain bound to atomic nuclei, and instead all the particles exist separately, the positively charged protons and the negatively charged electrons moving freely among one another like dancers at a very crowded ball who never quite take each other's hands. Light, in this environment, could not travel very far at all, because photons interact very strongly with free electrons through a process called Thomson scattering, which means that every time a photon tried to move through space, it would almost immediately encounter an electron and be deflected in some new direction, then encounter another electron and be deflected again, over and over, so that light was essentially trapped, bouncing endlessly from particle to particle in a kind of luminous fog that went nowhere. This era is sometimes called the recombination era, which is a name that has caused some gentle confusion over the years, because the prefix suggests that atoms were combining again after having been separated, when in fact this was the very first time in cosmic history that electrons and protons were joining together to form atoms at all. The name arose from the conventions of plasma physics, where the formation of neutral atoms from ionized gas is called recombination regardless of whether those atoms had ever existed before, and the terminology simply carried over into cosmology even though it does not quite fit the historical circumstances. So when you encounter the term recombination in discussions of the early universe, you may simply understand it to mean the time when atoms formed for the first time, when electrons finally settled into their orbits around protons, creating the neutral hydrogen that would eventually make up most of the ordinary matter in galaxies and stars and gas clouds throughout the cosmos. The key factor that allowed this recombination to occur was temperature, or more precisely, the gradual cooling of the universe as it continued to expand. In the earliest times, the universe was so hot that any atom that happened to form would immediately be torn apart again by the energetic photons surrounding it, the light itself carrying enough energy to knock electrons free from protons the moment they tried to bind together. But as the universe expanded, the radiation within it lost energy, stretching out to longer wavelengths and lower frequencies in exactly the way we discussed when exploring the nature of redshift, and gradually the temperature dropped, year by year, century by century, millennium by millennium, until eventually the photons no longer carried quite enough energy to ionize hydrogen atoms. The threshold temperature for this transition was approximately 3000 Kelvin, which is still enormously hot by everyday standards, roughly half the temperature of the surface of our Sun, but it was cool enough that the electrons could finally settle down and bind with protons without being immediately dislodged. It is worth mentioning that not all atoms formed at exactly the same moment, and that helium, which makes up roughly 24% of the ordinary matter in the universe by mass, actually underwent its own recombination slightly earlier than hydrogen. Helium nuclei, each containing 2 protons and typically 1 or 2 neutrons, have a stronger positive charge than hydrogen nuclei, and this means they can hold onto their electrons more tightly, binding them even at somewhat higher temperatures. So the helium in the universe became neutral first, followed some time later by the hydrogen, and this sequence of events is part of the detailed story of how the universe transitioned from its early plasma state to the neutral gas that would eventually form the first structures. But because hydrogen is so much more abundant than helium, making up roughly 75% of the ordinary matter, it is the recombination of hydrogen that truly marked the transformation of the universe from opaque to transparent, the moment when light was finally set free. This liberation of light is sometimes called photon decoupling, a term that captures the essential physics of what occurred. Before recombination, photons and matter were tightly coupled together, bound in a kind of electromagnetic dance where light could not move independently of the surrounding plasma. After recombination, once the electrons were safely tucked into their orbits around protons, the photons suddenly found themselves in a universe that was almost entirely transparent to their passage, and they could travel freely for the first time, streaming outward in all directions without being scattered or absorbed, carrying with them a record of the conditions that existed at that moment of their release. These are the very photons that we detect today as the cosmic microwave background, the ancient light that has been traveling toward us for nearly the entire history of the universe, and that finally arrives at our instruments after a journey of 13.8 billion years. The surface from which this light originated is called the surface of last scattering, a name that describes exactly what it represents, the last place where each photon scattered off a free electron before beginning its long journey across the cosmos. You might imagine this surface as something like the outer boundary of a cloud viewed from an aeroplane, the place where visibility suddenly changes from opaque to clear, where you can see the cloud itself but cannot see what lies hidden within its misty interior. When we look at the cosmic microwave background, we are looking at this surface of last scattering, and just as you cannot see through a cloud to whatever lies behind it, we cannot see through this primordial surface to whatever conditions existed in the universe before recombination occurred. The surface of last scattering is, in a very real sense, a wall beyond which our electromagnetic vision cannot penetrate, a cosmic photosphere that marks the boundary of the observable universe as far as light is concerned. The specific redshift at which this surface exists has been measured with considerable precision, and the value is approximately 1100, which we write as Z equals 1100. This means that the light we observe from the cosmic microwave background has been stretched by a factor of about 1100 since it was emitted, its wavelength multiplied by this enormous factor as the universe expanded around it during its long journey. At the time of emission, this light had a temperature of roughly 3000 Kelvin, placing it in the visible and infrared portions of the spectrum, but that same light now has a temperature of only 2.7 Kelvin, cooled by that same factor of 1100 into the microwave region where we observe it today. The precision with which we can measure this redshift, and the temperature it implies, is one of the triumphs of modern observational cosmology, giving us detailed information about conditions in the universe when it was less than 500,000 years old. One aspect of the surface of last scattering that sometimes surprises people is that it was not an instantaneous event, not a sharp boundary in time, but rather a gradual transition that occurred over an extended period. The recombination of hydrogen did not happen all at once throughout the universe, but proceeded gradually as the temperature dropped, with some regions becoming transparent before others, and with the probability of scattering decreasing slowly rather than switching off suddenly. This transition took approximately 100,000 years to complete, which means that the surface of last scattering has a certain thickness to it, a physical depth through which the transition from opaque to transparent occurred. This thickness corresponds to roughly 115,000 light-years, which is a substantial distance, larger than the diameter of many galaxies, though still quite thin compared to the vast scales of the observable universe. This finite thickness has consequences for what we can observe in the cosmic microwave background, because photons that scattered for the last time at slightly different depths within this transition zone carry slightly different information about the conditions at the time of their release. The thickness of the surface introduces a small amount of blurring into our observations, smoothing out the finest details that might otherwise be visible, though the effect is subtle and modern observations are precise enough to account for it in their analyses. Scientists sometimes speak of the visibility function, which describes the probability that a photon we observe today scattered for the last time at any particular moment during the recombination era, and this visibility function has a peak at the redshift of about 1100 but spreads out over a range that reflects the gradual nature of the transition. The existence of this surface of last scattering means that there is a fundamental limit to how far back in time we can see using electromagnetic radiation, a limit that is set not by the sensitivity of our instruments but by the opacity of the early universe itself. No matter how good our telescopes become, no matter how carefully we design our detectors, we will never be able to see beyond this cosmic photosphere with light, because there simply was no light traveling freely before this time, only photons trapped in an endless series of scatterings that prevented them from carrying information about any particular location or moment. The surface of last scattering is the oldest light in the universe, the first light that was able to travel freely, and everything beyond it is hidden from our electromagnetic view. This limitation is somewhat similar to the way the surface of the Sun prevents us from seeing into its interior using visible light. The Sun, too, has a photosphere, a surface beyond which it becomes opaque, and just as we cannot see the nuclear reactions occurring in the solar core by looking at the Sun with an ordinary telescope, we cannot see the conditions that existed in the very earliest moments of the universe by studying the cosmic microwave background. The analogy is not perfect, of course, because the Sun is a three-dimensional object with a well-defined center, while the surface of last scattering surrounds us in all directions at an immense distance. But the underlying principle is the same, the principle that opacity sets a limit on what electromagnetic radiation can reveal. This does not mean that the era before recombination is forever closed to scientific investigation, only that we must find other ways to study it, other messengers that can carry information through the opaque plasma of the early universe. Neutrinos, for instance, being only weakly interacting, would have decoupled from matter even earlier than photons, and a cosmic neutrino background is predicted to exist, though detecting it remains beyond our current technological capabilities. Gravitational waves, too, being ripples in the fabric of spacetime itself, would have passed through the early plasma without being absorbed or scattered, and detecting a primordial gravitational wave background would allow us to probe conditions in the universe at times far earlier than those accessible through light. But for now, the cosmic microwave background remains our most detailed window into the early universe, a snapshot of the cosmos as it was 380,000 years after its beginning, preserved in the gentle warmth of microwaves that arrive at our planet from every direction in the sky, telling us of a time when the universe first became transparent, when light first traveled freely, when the long darkness of the plasma era finally came to its quiet and gradual end. On a warm summer morning, the 30th of June in the year 2001, a Delta II rocket lifted off from Cape Canaveral in Florida, carrying with it a spacecraft that would spend the next 9 years quietly listening to the oldest light in the universe. This was the Wilkinson Microwave Anisotropy Probe, a mission that would measure the cosmic microwave background radiation with a precision that had never before been achieved, and in doing so, would reveal the fundamental properties of our universe with remarkable clarity. The launch itself was unremarkable in the way that successful space missions often are, the rocket performing exactly as intended, the spacecraft separating cleanly and beginning its long journey outward from Earth, toward a point in space where it would eventually settle into a gentle orbit and begin its patient work of mapping the ancient sky. The spacecraft was named after David Wilkinson, a physicist from Princeton University who had devoted much of his career to understanding the cosmic microwave background and who had been instrumental in designing this very mission. Wilkinson had worked on some of the earliest experiments to measure this faint radiation, and he understood perhaps better than most how much remained to be learned about the universe's earliest moments. Sadly, he did not live to see the full results of the mission that would bear his name, as he passed away from cancer in September of 2002, just over a year after the launch and several months before the first maps were released to the world. The decision to rename the spacecraft in his honor was a fitting tribute to a scientist who had spent decades listening carefully to the whispers of the early universe, and whose work had paved the way for this extraordinary endeavor. The probe traveled outward from Earth for approximately 3 months, using the Moon's gravity to help guide it toward its final destination, a location known as the second Lagrange point, or L2 for short. This is a remarkable place in space, situated roughly 1.5 million kilometers from Earth, on the side opposite to the Sun. At this point, the gravitational pull of the Sun and Earth combine in such a way that a spacecraft can remain in a stable orbit, always keeping Earth between itself and the Sun, and always maintaining roughly the same distance from our planet. This position offered several advantages for a mission designed to detect extremely faint microwave radiation, as the spacecraft could keep its sensitive instruments pointed away from the Sun, Earth, and Moon simultaneously, all of which produce interfering radiation that would otherwise contaminate the delicate measurements. The probe did not sit perfectly still at this point, but rather traced a gentle looping path around it, a kind of slow cosmic dance that kept it in the optimal position for observation while requiring very little fuel to maintain. The principal investigator for this mission was Charles Bennett, an astrophysicist from Johns Hopkins University who had spent years preparing for this moment. Bennett and his team had designed the spacecraft to address the limitations of earlier missions, particularly the Cosmic Background Explorer, which had made the first detection of tiny temperature variations in the microwave background a decade earlier. While COBE had demonstrated that these variations existed, its angular resolution was relatively coarse, able to distinguish features only about 7 degrees across, which is roughly 14 times the apparent diameter of the full Moon. The Wilkinson Microwave Anisotropy Probe was designed to see much finer detail, with an angular resolution of approximately 1/5 of a degree, which represented an improvement of about 45 times over its predecessor. This meant that where COBE had seen broad smudges of slightly warmer and cooler regions, the new probe would be able to discern much smaller structures, revealing patterns that contained profound information about the physics of the early universe. The spacecraft carried 2 back-to-back telescopes that collected microwave radiation and focused it onto sensitive detectors, which measured the tiny differences in temperature between different parts of the sky. These differences are almost impossibly small, amounting to variations of only about 1 part in 100,000 compared to the average temperature of the radiation, which is itself only about 2.7 degrees above absolute zero. To detect such minute fluctuations required extraordinary precision and stability, and the spacecraft was designed with great care to maintain consistent conditions throughout its long mission. The probe rotated slowly as it observed, sweeping its detectors across the sky in overlapping patterns that gradually built up a complete picture of the entire celestial sphere, with each point observed many times over to reduce errors and improve the reliability of the measurements. In February of 2003, less than 2 years after launch, the mission team released the first full-sky map of the cosmic microwave background as seen by the Wilkinson Microwave Anisotropy Probe. This image, rendered in colors showing the tiny temperature variations across the sky, was the most detailed portrait ever created of the universe as it appeared when it was only 380,000 years old, long before any stars or galaxies had formed. The patterns visible in this map were not random, but rather reflected the physical conditions present in the early universe, the distribution of matter and energy at a time when the cosmos was still a hot, dense plasma, just beginning to cool enough for atoms to form and for light to travel freely through space. These patterns, so gentle in their variations, so subtle in their structure, contained information that scientists could read like a kind of cosmic fingerprint, revealing fundamental truths about the nature of reality itself. Among the most significant findings was a precise determination of the age of the universe. By analyzing the patterns in the microwave background and combining them with other astronomical observations, the mission team concluded that the universe is approximately 13.77 billion years old, with an uncertainty of only about 40 million years in either direction. This was a remarkable achievement, reducing the uncertainty in this fundamental number to less than 1%, and giving humanity its most accurate estimate yet of how long ago everything began. The age was determined not by measuring the universe directly, as one might measure the rings of a tree, but rather by understanding how the patterns in the microwave background depend on the rate at which the universe has expanded over time, and working backward to determine when that expansion must have begun. The data also confirmed with high precision that the geometry of the universe is flat, or very nearly so. In a flat universe, parallel lines remain parallel forever. The angles of a triangle add up to exactly 180 degrees, and the familiar rules of Euclidean geometry apply on the largest possible scales. This might seem like a simple or even obvious result, but it was not guaranteed, as the equations of general relativity allow for universes with positive or negative curvature, in which the rules of geometry would be different. The flatness of the universe has profound implications for its past and future, and is connected to deep questions about why the universe has the particular properties that it does. Perhaps the most striking finding concerned the composition of the universe, which turned out to be quite different from what one might naively expect. The ordinary matter that makes up stars and planets and people, the atoms and molecules that we interact with every day, accounts for only about 4% of the total energy content of the cosmos. Another 23% consists of dark matter, a mysterious substance that does not emit or absorb light, but whose gravitational influence can be detected through its effects on visible matter and on the patterns in the cosmic microwave background itself. The remaining 73%, the overwhelming majority, is attributed to something even more enigmatic called dark energy, a property of space itself that causes the expansion of the universe to accelerate over time. These proportions were determined by careful analysis of the microwave background patterns, combined with other observations, and they painted a picture of a universe that is mostly made of things we do not yet understand. The power of the Wilkinson microwave anisotropy probe data lay not just in the images themselves, but in the mathematical analysis of the patterns they contained. Scientists examined the temperature variations by breaking them down into waves of different sizes, much as a complex musical sound can be decomposed into individual notes of different pitches. When plotted on a graph showing the strength of the variations at each angular scale, the data revealed a distinctive series of peaks and troughs, known as acoustic peaks, which correspond to sound waves that once traveled through the hot plasma of the early universe. The position and height of these peaks are determined by the physical conditions at that time, including the density of matter and energy, the rate of expansion, and other fundamental parameters. By measuring these peaks precisely, scientists could work backward to determine what those conditions must have been, extracting a wealth of information from the subtle wiggles in a single graph. The mission continued to collect data for 9 years, far longer than originally planned, gradually building up an increasingly precise picture of the microwave sky. Each additional year of observations allowed the team to reduce the noise in their measurements and to cross-check their results for consistency, ensuring that the patterns they were seeing were truly cosmic in origin rather than artifacts of the instrument or other sources of interference. The final data release, based on observations collected through 2010, represented the culmination of this long effort, providing a legacy dataset that scientists continue to analyze and learn from to this day. During the course of the mission, an intriguing and somewhat controversial feature was noticed in the data, which came to be known informally as the axis of evil, a name chosen partly in jest but reflecting a genuine puzzle. The temperature fluctuations in the microwave background, when examined at the very largest scales, appeared to show unexpected alignments, with certain patterns oriented in a particular direction in the sky rather than being randomly distributed as theoretical models predicted. This alignment seemed to correlate with the plane of the solar system and the direction of Earth's motion through space, which was surprising and difficult to explain, since the cosmic microwave background originates from a time and place completely unrelated to our local environment. Some scientists suggested that this might indicate unknown systematic errors in the data, perhaps some subtle contamination from our own solar system that had not been properly removed. Others proposed that it might be a genuine cosmological effect, pointing to new physics beyond the standard model. The debate continued for years, and while subsequent missions have provided additional data, the question has never been entirely resolved, remaining as one of those gentle mysteries that occasionally arise when we peer deeply into the nature of things. Throughout its mission, the Wilkinson microwave anisotropy probe demonstrated the power of patient, careful observation, collecting photons that had been traveling through space for nearly 14 billion years and using them to reconstruct the conditions of the infant universe. The spacecraft itself was modest in size and cost compared to many astronomical missions, but its scientific return was extraordinary, fundamentally changing our understanding of cosmology and providing a foundation upon which later missions would build. The data it collected continues to be cited and analyzed, a testament to the quality of the measurements and the care with which the mission was conducted. And so the probe completed its work, drifting quietly at the second Lagrange point, having fulfilled its purpose of mapping the faint afterglow of creation with unprecedented precision. The universe it revealed was ancient and vast, mostly made of substances we cannot see or touch, governed by forces we are still working to understand. But it was also a universe that could be measured and described, its properties written in the patterns of light that have been traveling toward us since before the first stars were born, patterns that the Wilkinson microwave anisotropy probe captured with patient and meticulous care. On the 14th of May, 2009, in the warm equatorial air of French Guiana, an Ariane 5 rocket lifted away from the launch complex at Kourou, carrying with it two of the most sophisticated astronomical instruments that European engineering had ever produced. One of these spacecraft was the Herschel Space Observatory, designed to observe the universe in infrared light, and the other was a mission that would come to represent the most precise measurement of the cosmic microwave background radiation ever attempted, a satellite named Planck, after the German physicist Max Planck, whose work on the nature of light and energy helped to establish the foundations of quantum mechanics more than a century earlier. The two spacecraft shared their journey into space, riding together atop the rocket before separating to pursue their different orbits and their different scientific objectives, and in this quiet way, with the rumble of engines fading into the blackness above the South American coastline, Europe's ultimate cosmic microwave background observatory began its work. The Planck satellite was a mission of the European Space Agency, developed over more than 15 years of careful planning and technological refinement, and it represented the accumulated expertise of scientific institutions across Europe and beyond. The mission brought together hundreds of researchers, engineers, and technicians, each contributing their particular knowledge to a project whose ambition was nothing less than to produce the most detailed map of the early universe that human instruments could achieve. The satellite carried two primary instruments, each designed to observe the cosmic microwave background at different frequencies, and each representing a remarkable achievement in the development of sensitive detectors capable of measuring the faintest variations in temperature across the entire sky. These instruments were the high-frequency instrument, which was led by the French astrophysicist Jean-Luc Puget, and the low-frequency instrument, which was led by the Italian astrophysicist Rino Mandolisi, and together these two devices would survey the heavens with a precision that previous missions could only approximate. The journey from Earth to the satellite's operational location took several weeks, during which the spacecraft traveled to a point in space known as the second Lagrange point, or L2, a gravitationally stable position located approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the satellite could maintain a fixed orientation relative to both the Earth and the Sun, keeping its sensitive instruments perpetually shielded from the warmth and light of our star while it slowly rotated to scan the entire sky. The choice of this orbital position was essential to the mission's success, for the cosmic microwave background radiation is extraordinarily faint, and any stray heat from the Sun or the Earth would overwhelm the delicate signals that the instruments were designed to detect. In the cold darkness of L2, far from the thermal noise of our planet, Planck could listen to the whisper of the early universe with unprecedented clarity. Perhaps the most remarkable aspect of the Planck satellite was its cooling system, a technological marvel that allowed the spacecraft to achieve temperatures colder than anything else known to exist in the natural universe. The high-frequency instrument required cooling to a temperature of just 1/10 of a degree above absolute zero, approximately 0.1 Kelvin, making it the coldest known object in space during its period of operation. Achieving such extreme cold required a cascade of cooling stages, each one bringing the temperature lower than the last, beginning with passive radiators that rejected heat into space, continuing through mechanical coolers that used the compression and expansion of helium gas, and culminating in a dilution refrigerator that mixed two isotopes of helium in a process that extracted the final remnants of thermal energy from the instrument. This cooling system represented decades of engineering development, and its successful operation in the vacuum of space, more than 1,000,000 kilometers from any possibility of repair or adjustment, stands as a quiet testament to the care and precision with which the mission was designed. The detectors at the heart of the high-frequency instrument were devices known as spiderweb bolometers, and their name derives from their delicate physical structure, which resembles the pattern of a spider's web when viewed under magnification. These bolometers work by absorbing microwave radiation and converting it to a tiny amount of heat, which is then measured with extraordinary sensitivity by monitoring the change in electrical resistance of a small thermometer attached to the detector. The spiderweb design minimizes the mass of the absorbing element, which allows it to respond more quickly to changes in the incoming radiation, and the thin strands of the web-like structure reduce the noise caused by cosmic ray particles striking the detector. When cooled to 0.1 Kelvin, these bolometers could detect temperature differences in the cosmic microwave background of just a few millionths of a degree, variations so subtle that they would be utterly imperceptible to any instrument operating at ordinary temperatures. The low-frequency instrument operated at somewhat higher temperatures, though still far colder than any natural environment on Earth, and it used a different type of detector known as a radiometer. These devices amplified the microwave signals using transistors cooled to approximately 20 Kelvin, and they were designed to observe the cosmic microwave background at longer wavelengths where the spiderweb bolometers were less sensitive. Together, the two instruments covered a range of frequencies from 30 GHz to nearly 900 GHz, allowing the satellite to distinguish the cosmic microwave background from other sources of microwave emission, such as dust within our own galaxy or radiation from distant galaxies, which emit at different characteristic frequencies. This multi-frequency capability was essential for producing a clean map of the primordial radiation, free from contamination by the foreground sources that lie between us and the edge of the observable universe. The satellite began its scientific observations shortly after reaching its operational orbit, and over the following months it traced a slow spiral pattern across the sky, recording the temperature of the cosmic microwave background in every direction. The spacecraft rotated once per minute, sweeping its instruments across a great circle on the sky, while the axis of this rotation itself shifted gradually over time, so that eventually every part of the heavens would be observed multiple times from different angles. This scanning strategy allowed the scientists to cross-check their measurements and to identify any systematic errors that might arise from the particular orientation of the satellite or the behavior of its instruments. By the time the mission was complete, Planck had surveyed the entire sky more than 4 times, building up a detailed picture of the cosmic microwave background with over 50 million individual measurements. The first all-sky image from the Planck satellite was released to the public in July of 2010, and it showed the entire universe wrapped around a single oval projection, painted in colors that represented the tiny variations in temperature across the sky. The image was beautiful in its complexity, showing the mottled pattern of hot and cold spots that are the frozen remnants of sound waves in the primordial plasma, and it also revealed the bright band of emission from our own Milky Way galaxy, which had to be carefully removed from the data before the underlying cosmic signal could be studied. This first image was only a preliminary result, a demonstration of the satellite's capabilities rather than a final scientific product, but it hinted at the remarkable precision that the full analysis would eventually achieve. The detailed cosmological results from Planck were first published in March of 2013, and they represented the most precise determination of the fundamental parameters of our universe that had ever been made. Among these results was a new estimate of the age of the universe, which Planck determined to be approximately 13.82 billion years, slightly older than the previous estimate from the WMAP satellite, which had suggested an age closer to 13.77 billion years. This difference of 50 million years, while seemingly small compared to the vastness of cosmic time, was significant because it reflected the improved precision of the Planck measurements, and it had implications for our understanding of the rate at which the universe is expanding and the processes by which the first stars and galaxies formed. The Planck results also indicated that the universe contains slightly more ordinary matter and dark matter than WMAP had suggested, and correspondingly less dark energy, the mysterious component that is causing the expansion of the universe to accelerate. These refinements to our cosmic inventory may seem like minor adjustments, but they accumulate into a picture of the universe that differs in subtle but important ways from what earlier observations had suggested. One of the most important aspects of the Planck results concerned the very earliest moments of the universe, the hypothetical period of cosmic inflation during which the universe expanded by an enormous factor in an unimaginably brief instant of time. The theory of inflation predicts that this rapid expansion should have generated gravitational waves, ripples in the fabric of spacetime itself, which would have left a characteristic imprint on the cosmic microwave background in the form of a particular pattern of polarization. The strength of this imprint is described by a quantity known as the tensor-to-scalar ratio, and measuring this ratio was one of the key scientific goals of the Planck mission. The results from Planck placed stringent upper limits on the tensor-to-scalar ratio, constraining it to be much smaller than some of the simpler models of inflation had predicted, and this finding challenged theorists to develop more sophisticated versions of inflationary theory that could accommodate the observations. The search for the gravitational wave signature of inflation continues to this day, and while Planck did not detect it, the limits it established have shaped the direction of research in this fundamental area of cosmology. The final data release from the Planck mission came in July of 2018, incorporating the full set of observations from both instruments and the most refined analysis techniques that the collaboration had developed over the years. This legacy dataset represents the definitive record of the cosmic microwave background as seen by Planck, and it will continue to be studied by researchers for decades to come, yielding new insights into the physics of the early universe long after the satellite itself has fallen silent. The mission formally concluded when the satellite exhausted the helium coolant that was necessary to keep the high-frequency instrument at its operating temperature, and without this cooling, the bolometers could no longer detect the faint signals from the cosmic microwave background. The satellite was placed into a safe parking orbit around the Sun, where it will drift quietly for millions of years, a monument to human curiosity and the desire to understand our origins. Among the many features revealed in the Planck data, one has attracted particular attention and speculation: a region of the sky known informally as the cold spot. This is an unusually large area where the temperature of the cosmic microwave background is slightly lower than would be expected from the normal statistical fluctuations in the primordial radiation, and its existence has prompted a variety of explanations from cosmologists seeking to understand its origin. One possibility is that the cold spot is caused by a supervoid, an exceptionally large region of space that contains fewer galaxies and less matter than average, through which the cosmic microwave background photons have passed on their long journey to Earth. Such a void, estimated to be approximately 1.8 billion light-years across, would cause the photons to lose a small amount of energy as they traverse the relatively empty space, resulting in a slightly cooler temperature when they finally reached our instruments. Other explanations have been proposed as well, some of them involving more exotic physics such as collisions between our universe and other universes in a hypothetical multiverse, though these ideas remain highly speculative and are not supported by any definitive evidence. The cold spot remains an intriguing puzzle, a small blemish on the otherwise remarkably uniform canvas of the cosmic microwave background, and its true nature may not be understood for many years yet. The total cost of the Planck mission was approximately 700 million euros, an investment shared among the member states of the European Space Agency and the scientific institutions that participated in the development and operation of the instruments. This sum, while substantial by the standards of most human endeavors, represents a tiny fraction of what nations spend on other activities, and it has yielded a scientific return that is difficult to quantify in monetary terms. The Planck satellite has given us the most detailed picture of the infant universe that we are ever likely to obtain from measurements of the cosmic microwave background, a portrait of the cosmos as it appeared just a few 100,000 years after the Big Bang, when the fundamental structures that would eventually become galaxies and stars and planets were just beginning to emerge from the primordial chaos. It is a gift of knowledge, offered by one generation to all those who will follow, and it will be studied and appreciated for as long as human beings continue to look up at the sky and wonder about the nature of existence. In the very beginning, when the universe was still impossibly young and impossibly hot, there was music. Not music as we might ordinarily think of it, with instruments and melodies, but something far more fundamental, and in its own quiet way, far more beautiful. Sound waves were traveling through the cosmos, rippling across the entire observable universe in a symphony that would play for nearly 400,000 years before falling silent forever. These waves left their mark, frozen into the fabric of space itself, and tonight we shall trace their gentle story together, following the echoes of this ancient music as it reverberates through everything we see in the night sky. To understand these cosmic sound waves, we must first return to that era when the universe was a plasma, a time when space was filled with a hot, dense soup of matter and radiation, all bound together in intimate connection. In this plasma, photons could not travel freely, for they were constantly scattering off the electrically charged particles that surrounded them, bouncing from electron to electron in an endless diffused dance. The universe was opaque then, like a thick fog illuminated from within, and light and matter moved together as one substance, coupled by their continuous interactions. It is within this coupled fluid that our sound waves were born, and it is the nature of this fluid that gave them their particular character. Sound, in its most essential form, is simply a wave of compression and rarefaction traveling through a medium, any medium at all, whether it be air or water or the plasma of the early universe. What makes sound possible is the ability of pressure to push material outward from regions of higher density to regions of lower density, creating oscillations that propagate through the substance as a whole. In the early cosmic plasma, there were indeed regions of slightly higher density, seeded by the tiny quantum fluctuations we discussed earlier, and these regions became the birthplaces of cosmic sound. Gravity pulled matter toward these denser spots, attempting to collapse them further, while the pressure of radiation pushed outward, resisting the gravitational pull. This interplay between gravity and radiation pressure created oscillations, waves of compression and expansion that traveled outward through the plasma like ripples on an incomprehensibly vast pond. The speed at which these waves traveled was remarkable, approximately 170,000 meters per second, which is more than half the speed of light itself. This extraordinary velocity arose because the plasma was so incredibly hot, and sound speed depends upon temperature, with hotter materials allowing faster propagation. In air at room temperature on Earth, sound travels at roughly 340 meters per second, a gentle pace compared to this cosmic rush. But in the fierce heat of the early universe, where temperatures reached millions of degrees, the sound waves raced through space at speeds we can scarcely imagine in our everyday experience. Yet even at this tremendous pace, the waves could only travel so far before the universe changed around them, and this finite travel distance would prove to be one of the most important features they left behind. For nearly 400,000 years, these sound waves traveled, expanding outward from each primordial density enhancement, carrying matter and radiation together in their oscillations. Some regions were caught in the compression phase, squeezed together by the wave, while others were in the rarefaction phase, stretched thin as the wave passed through. The pattern was complex but orderly, governed by the simple physics of an oscillating fluid, and if we could somehow have watched the universe during this epoch, we would have seen a shimmering, pulsating sea of plasma, everywhere vibrating with these ancient tones. The gravity of the dark matter, which does not interact with radiation and therefore does not feel the pressure that pushes ordinary matter about, provided a steady scaffolding around which these oscillations occurred, the dark matter halos sitting quietly while the ordinary matter sloshed back and forth within them. And then, at the moment of recombination, the music stopped. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, the photons were suddenly released from their imprisonment, free to stream through space without scattering. The radiation pressure that had been pushing back against gravity vanished almost instantly, for photons no longer coupled to matter once that matter became electrically neutral. The oscillations ceased mid-note, frozen in whatever phase they happened to occupy at that precise moment. Some regions were caught at maximum compression, others at maximum rarefaction, and still others somewhere in between, and this pattern was simply preserved, locked into the distribution of matter as the universe continued to expand. The sound waves did not fade away gradually as earthly sounds do, but rather stopped all at once, their pattern imprinted permanently on the cosmos. This freezing of the oscillation pattern created what physicists call baryon acoustic oscillations, often abbreviated to BAO, and these frozen waves have become one of the most powerful tools we have for understanding the universe. The characteristic size of the oscillations, determined by how far sound could travel before recombination, corresponds to a specific distance that we can calculate with considerable precision. In the early universe, this distance was approximately 450,000 light-years, but as the universe has expanded over the past 13.8 billion years, this scale has stretched along with everything else. In today's expanded universe, the characteristic distance has grown to approximately 220 megaparsecs, which is about 720 million light-years, a span so vast that it encompasses many thousands of galaxies. This characteristic scale appears in the cosmic microwave background as a particular angular size on the sky, and finding this size tells us something profound about the geometry of the universe itself. If the universe has positive spatial curvature, like the surface of a sphere, then distant objects appear larger than they would in flat space, just as the continents on a globe appear distorted when we try to represent them on a flat map. If the universe has negative curvature, like a saddle, then distant objects appear smaller. But if the universe is flat, with the ordinary geometry we learn about in school, then objects appear at exactly the angular size we would naively expect from their distance and physical extent. The first peak in the cosmic microwave background's power spectrum, appearing at an angular multipole of approximately 220, corresponding to an angular scale of about 1 degree on the sky, tells us that the universe is indeed flat, or very nearly so. This is a remarkable finding, and it agrees with the predictions of inflationary theory, which suggests that any primordial curvature would have been stretched to insignificance by the rapid expansion of the early moments. The power spectrum of the cosmic microwave background contains not just one peak but several, a series of gentle undulations that encode a wealth of information about the early universe. The first peak tells us about geometry, as we have just discussed, but the heights and positions of the subsequent peaks tell us about the composition of the cosmos itself. The second peak, appearing at roughly twice the multipole of the first, is particularly sensitive to the density of ordinary matter, the baryons that make up atoms and molecules and everything we can see and touch. The ratio of the first peak's height to the second peak's height reveals how much of the universe consists of this familiar material, and the answer, as it turns out, is only about 5%. The third peak, appearing at still higher multipoles, helps to constrain the density of dark matter, that mysterious substance that does not interact with light but whose gravitational influence shapes the large-scale structure of the cosmos. By carefully measuring the heights and positions of all these peaks, cosmologists have determined that dark matter constitutes roughly 27% of the universe's total energy content, with the remaining 68% being the even more mysterious dark energy that drives the accelerating expansion of space. The analogy to musical instruments is perhaps not misplaced here, for the physics of organ pipes shares much in common with these cosmic oscillations. An organ pipe of a given length resonates at particular frequencies, its fundamental tone and a series of overtones, with the pitch determined by how sound waves reflect and interfere within the pipe's confines. Different lengths of pipe produce different notes, and together they can create the rich harmonic textures we associate with cathedral music. The early universe was like a collection of pipes of every possible length, each oscillating at frequencies determined by its size and by the properties of the plasma through which the sound traveled. The largest oscillations, corresponding to the longest pipes, produced the fundamental tone, which appears as the first peak in the power spectrum, while smaller oscillations produced the higher harmonics, appearing as the subsequent peaks. When recombination occurred, all these oscillations were frozen simultaneously, like an organist lifting their hands from the keyboard and holding the pedals, leaving every pipe sounding its last note in eternal sustaining silence. Not all of the primordial sound waves survived to be frozen at recombination. However, for the smallest oscillations were gradually erased by a process called diffusion damping, sometimes known as silk damping after the physicist Joseph Silk who first described it in detail. On very small scales, the coupling between photons and baryons was not perfectly tight, and photons could gradually leak out of overdense regions, carrying energy and momentum away with them. This leakage smoothed out the smallest fluctuations, blurring the fine details of the primordial pattern like fog softening a distant landscape. The characteristic scale below which this damping became significant depends on the mean free path of photons in the plasma and on the time available before recombination, and it appears in the power spectrum as a gradual decline in power at high multipoles. Joseph Silk's careful theoretical work, carried out in the late 1960s, predicted this damping before it was observed, and its detection in the cosmic microwave background data confirmed our understanding of the physics governing the early universe. The frozen sound waves did not remain merely a pattern in the cosmic microwave background, for they became the seeds around which the large-scale structure of the universe grew. The regions of maximum compression at recombination contained slightly more matter than their surroundings, and over the following billions of years, gravity slowly amplified these enhancements, drawing more and more material into the overdense regions. Galaxy clusters formed preferentially at these locations, and today, billions of years later, we find that galaxies are not distributed randomly through space but are instead slightly more likely to be found separated by that characteristic distance of approximately 150 megaparsecs in comoving coordinates, or about 720 million light-years when we account for the expansion that has occurred since the oscillations froze. This preferred separation shows up as a subtle excess in the correlation function of galaxy positions, a gentle bump that astronomers can measure by surveying millions of galaxies and carefully analyzing their three-dimensional distribution. The Sloan Digital Sky Survey, an ambitious project to map large portions of the sky and measure the positions and properties of countless celestial objects, provided some of the first clear detections of this baryon acoustic oscillation signal in galaxy distributions. By measuring the positions of hundreds of thousands of galaxies and computing their statistical correlations, astronomers found the expected excess at the characteristic BAO scale, confirming that the frozen sound waves of the early universe do indeed pervade the cosmic structure we observe today. This detection has become an invaluable tool for cosmology, for the BAO scale serves as a standard ruler that we can use to measure distances across the universe. If we know the true physical size of the ruler, and we can measure its apparent angular size at various redshifts, then we can determine how the universe has expanded over time, probing the mysterious dark energy that dominates the cosmos in the present epoch. And so the music of the early universe, though it fell silent billions of years ago, continues to echo through everything we see, written in the patterns of the oldest light and in the gentle clustering of galaxies across the cosmic web. These frozen sound waves carry information about the composition and geometry of the cosmos, about the interplay between ordinary matter and dark matter and radiation, about the physics that govern the universe in its earliest moments. When we look at the peaks in the cosmic microwave background's power spectrum, we are seeing the final chord of a symphony that played for 400,000 years, now preserved forever in the temperature fluctuations of the sky, a gentle melody written in microkelvins that tells us who we are and where we came from. The universe, it seems, began not with a bang but with a song, and though the singer has long since fallen silent, the song itself endures, frozen in light, waiting patiently across the ages for anyone who might wish to listen. And now we turn our attention to some of the quieter puzzles that remain within our observations of the cosmic microwave background, those small peculiarities and gentle anomalies that continue to interest researchers even as the broader picture has become remarkably clear. And these are the sorts of questions that do not demand urgent resolution but rather invite patient contemplation, the kind of slow wondering that suits a restful state of mind, for science is often most honest when it acknowledges what it does not yet fully understand, and there is something rather peaceful in knowing that the universe still holds a few soft mysteries within its ancient light. In the year 2004, a team of researchers led by M. Cruz and colleagues identified something unusual in the cosmic microwave background maps, a region of sky that appeared noticeably colder than its surroundings, and this feature has come to be known simply as the CMB cold spot, a name that describes it quite accurately without any embellishment, for it is indeed a spot that is cold, remarkably so by the standards of these faint temperature variations we have been discussing. Throughout our time together, and it sits in the direction of the constellation Eridanus, which is a long and winding river of stars visible from the southern hemisphere and from lower northern latitudes, a constellation named for a mythological river, though of course the cold spot itself lies far beyond any stars we can see with our eyes, out at the very edge of the observable universe where the microwave light has been traveling for nearly 14 billion years. This cold spot measures approximately 70 microkelvins colder than the average temperature of the cosmic microwave background, which you will recall sits at about 2.725 Kelvin, and so we are speaking of a temperature difference of roughly 70 millionths of a single degree, a variation so extraordinarily subtle that it would be entirely imperceptible to any ordinary thermometer. And yet against the smooth and gentle undulations of the CMB, this region stands out with a quiet but unmistakable presence, rather like a slightly deeper pool of stillness in an already calm lake, and the spot spans approximately 5 degrees across the sky, which is to say about 10 times the apparent width of the full moon as seen from Earth, making it a rather substantial feature in angular terms, even though it represents only a tiny fraction of the full celestial sphere. What makes this cold spot particularly interesting to cosmologists is not merely that it exists, for we would expect some regions to be somewhat colder and others somewhat warmer simply due to the random nature of the primordial fluctuations, but rather that it appears to be somewhat larger and colder than our standard models would typically predict, sitting at the outer edges of what we might consider statistically comfortable, not so extreme as to definitively contradict our understanding, but unusual enough to warrant careful consideration and continued study, the sort of gentle outlier that keeps researchers thoughtfully engaged without causing any particular alarm. Several explanations have been proposed for the origin of this cold spot, and each carries its own quiet plausibility, inviting us to consider different possibilities without rushing toward any premature conclusion, and the first of these explanations involves what is known as the Eridanus supervoid, a hypothesis suggesting that the cold spot corresponds to an unusually large and empty region of space lying between us and the surface of last scattering, a vast bubble of relative emptiness where the density of galaxies and dark matter falls below the cosmic average, stretching perhaps 300 million light-years across or even more, and such a void could in principle cause the observed temperature dip through a subtle effect related to the expansion of the universe. For as photons of the cosmic microwave background travel through such an underdense region, they would experience a slight net loss of energy due to the changing gravitational conditions during their passage, leaving them ever so slightly cooler than they would otherwise have been. Another possibility that has been carefully considered involves what cosmologists call a cosmic texture, which is a type of topological defect that might have formed during the very early moments of the universe when various symmetries were breaking in the cooling aftermath of the initial expansion, and these textures are quite different from the cosmic strings we mentioned elsewhere, being more like knots or tangles in the fabric of certain fields that pervaded the early cosmos, and if such a texture existed and then unwound or collapsed, it could have left behind a characteristic imprint on the cosmic microwave background, a cold spot with particular properties that might match what we observe in the Eridanus region, though this explanation requires the existence of physical phenomena that remain somewhat speculative and unconfirmed by other observations. There is also the straightforward possibility that the cold spot is simply a statistical fluke, an unlikely but not impossible outcome of the random processes that generated the primordial fluctuations, for when we observe the entire sky and identify the coldest or most unusual region, we are in some sense selecting for extremes, and rare events do occasionally occur even when they are not expected, much as a very long sequence of fair coin tosses will sometimes produce an unexpectedly long run of heads or tails, and this explanation has the virtue of not requiring any new physics or unusual cosmic structures, though it does leave some researchers feeling that the cold spot is perhaps too unusual to dismiss so readily as mere chance. And then there is the most speculative explanation of all, the suggestion that the cold spot might represent evidence of another universe's gravitational influence on our own, a gentle tug from beyond the boundaries of our observable cosmos, and this idea emerges from certain theoretical frameworks in which our universe is just one bubble among many in a vast multiverse, and if another bubble universe happened to form in close proximity to our own during the inflationary epoch, its gravitational effects might have left a subtle imprint on the matter and radiation within our universe, creating a region that appears anomalously cold in the microwave background, and while this explanation captures the imagination, it remains highly speculative and difficult to test with current observations, sitting at the boundary between established physics and theoretical conjecture. Beyond the cold spot itself, there are other curious patterns in the cosmic microwave background that have attracted attention and earned rather colorful names from the researchers who study them, and one of these is known informally as the axis of evil, a term coined in 2005 by physicists Kate Land and Joao Magalhães. And despite its dramatic name, this feature is really quite a subtle alignment that most of us would never notice without sophisticated mathematical analysis. 4. It concerns the way that certain large-scale patterns in the CMB appear to line up with the plane of our solar system and with the direction of Earth's motion through space, an alignment that seems improbable if the primordial fluctuations were truly random and if our particular location in the cosmos holds no special significance. To understand what this means, we need to recall that the temperature variations in the cosmic microwave background can be decomposed into different mathematical components called multipole moments, much as a complex musical chord can be broken down into its constituent pure tones, and the lowest of these multipoles describe the largest scale patterns on the sky, with the quadrupole representing variations with 2 peaks and 2 troughs around the celestial sphere, and the octupole representing patterns with 4 peaks and 4 troughs. And what Land and Magalhães noticed was that these particular multipole components seemed to share a common axis of orientation, and furthermore that this axis pointed in a direction suspiciously close to the plane in which the planets of our solar system orbit the Sun, which should have absolutely nothing to do with the cosmic microwave background originating from the distant reaches of the universe. This apparent alignment has been confirmed by subsequent observations and analyses, and it remains something of a puzzle, for our standard cosmological models would predict that the orientation of these multipoles should be essentially random with respect to any local reference frame, and the probability of such an alignment occurring by chance alone appears to be quite small, though precisely how small depends on the details of how one performs the statistical analysis, and various researchers have debated whether this constitutes a genuine anomaly requiring new physics or whether it might be explained by subtle systematic effects in the observations or in the methods used to separate the CMB signal from foreground contamination caused by our own galaxy, and so the axis of evil remains a gentle thorn in the side of standard cosmology, not quite painful enough to cause serious alarm but persistent enough to remain interesting. Related to this is another curiosity known as the hemispherical power asymmetry, which refers to the observation that one half of the sky appears to have slightly stronger temperature fluctuations than the other half, as if the volume of the cosmic microwave background had been turned up ever so slightly on one side and down on the other, and this asymmetry is again quite subtle, amounting to only a few % difference in the amplitude of the fluctuations between the two hemispheres, but it appears consistently in multiple independent analyses of the data from both the WMAP and Planck satellites, suggesting that it is a real feature of the sky rather than an artifact of the instruments or analysis methods. And like the axis of evil, it challenges our expectation that the universe should look statistically the same in all directions, an assumption known as isotropy that underlies much of our standard cosmological framework. Let us also take a moment to appreciate one of the earlier balloon-borne experiments that contributed to our understanding of the cosmic microwave background, an experiment known as Boomerang, which flew from a base in Antarctica during 2 campaigns in 1998 and 2003, carried aloft by a large helium balloon that circled the frozen continent at an altitude of nearly 40 kilometers, where the thin and dry atmosphere allowed the sensitive detectors to observe the microwave sky with minimal interference from water vapor, and this experiment produced detailed maps of a portion of the cosmic microwave background that revealed for the first time the characteristic pattern of acoustic peaks in the power spectrum, those gentle undulations that tell us about the geometry and composition of the universe. And the Boomerang results provided some of the earliest strong evidence that the geometry of the universe is very close to flat, meaning that parallel lines remain parallel over cosmic distances and that the total energy density of the universe sits at or very near the critical value that separates eternal expansion from eventual recollapse, a finding that has since been confirmed and refined by the satellite missions that followed. And finally, we come to one of the most actively discussed tensions in contemporary cosmology, a gentle disagreement between different methods of measuring how fast the universe is expanding, a quantity known as the Hubble constant that describes the rate at which distant galaxies recede from us due to the overall stretching of space, and when cosmologists use the cosmic microwave background to infer this expansion rate, working backward from the detailed patterns in the ancient light to determine the parameters of the cosmological model that best fits the data, they arrive at a value of approximately 67.4 kilometers per second per megaparsec, meaning that a galaxy located 1 megaparsec away which is about 3.3 million light-years, would be receding from us at roughly 67 kilometers per second due to the expansion of the universe alone. However, when other researchers measure the expansion rate more directly, using observations of particular types of stars called Cepheid variables or exploding stars called Type Ia supernovae in relatively nearby galaxies, they consistently find a somewhat higher value of approximately 73 kilometers per second per megaparsec. And this difference of about 8 or 9% between the two approaches has persisted even as both types of measurements have become more precise, which is rather the opposite of what one would hope, for usually when measurements disagree we expect that improving their accuracy will bring them into alignment, but in this case the better we measure, the more clearly we see that the disagreement is real. This tension between the CMB-derived Hubble constant and the local measurements might indicate the presence of new physics that our standard cosmological model does not yet include, perhaps additional types of particles that affected the early universe, or subtle modifications to our understanding of dark energy or gravity, or it might instead point to systematic errors in one or both measurement approaches that have not yet been identified and corrected, and researchers continue to investigate both possibilities with careful attention, checking and rechecking their methods, exploring alternative explanations, and designing new observations that might help resolve the discrepancy. And this is the patient and unhurried work of science, the gradual refinement of understanding through persistent inquiry, and there is no need to rush toward a conclusion when the questions themselves are so gently interesting. And so we find that even within our remarkably successful picture of the cosmic microwave background, there remain these small unexplained features, these gentle anomalies and quiet tensions that remind us of how much we have yet to learn, and rather than being troubling, these mysteries are in their own way quite comforting, for they assure us that the universe has not yet given up all its secrets, that there will always be more to discover for those who wish to look, and in the meantime the ancient light continues to wash over us, carrying its faint warmth from the distant past, and we can rest easy knowing that the cosmos holds its puzzles with patience, waiting for us to understand them in our own time, whenever we are ready. At the very bottom of the world, on a vast plateau of ice that stretches in every direction toward horizons that never seem to arrive, there stands a collection of scientific buildings known as the Dark Sector Laboratory, and it is here, in one of the most remote and inhospitable places on Earth, that a team of researchers from Harvard and several other institutions installed a telescope called BICEP 2, which is a name that stands for Background Imaging of Cosmic Extragalactic Polarization, and the numeral 2 indicates that this was the second generation of an instrument designed to peer into the faint afterglow of the early universe with a very particular and ambitious goal in mind. The South Pole, for all its bitter cold and its months of total darkness, turns out to be one of the finest places on our planet to conduct this kind of observation, because the air there is exceptionally dry and stable, with almost no water vapor to absorb the delicate microwave signals drifting in from the edge of observable space, and the telescope could stare at the same patch of sky for long periods without the complications that plague observatories at lower latitudes, where the atmosphere is thicker and the weather far more changeable. The team was led by John Kovac, an astronomer at the Harvard Smithsonian Center for Astrophysics, and the question they were trying to answer was one of the deepest and most consequential in all of cosmology, namely whether it might be possible to detect the imprint of gravitational waves that had been generated during the first unimaginably tiny fraction of a second after the Big Bang, during a period that theorists call cosmic inflation, when the universe expanded at a rate so rapid and so extreme that it defies any ordinary sense of scale or speed. If such waves existed, and if they had left their mark on the cosmic microwave background radiation, then finding that mark would constitute perhaps the most profound confirmation of inflationary theory ever achieved, a kind of direct glimpse into processes that occurred when the universe was only about 10 to the power of negative 36 seconds old, which is a number so small that writing it out would require placing 35 zeros after a decimal point before arriving at the digit 1. The specific signature they were searching for is called B-mode polarization, and to understand what this means, it helps to recall that light, including the microwave light of the cosmic background, can vibrate in particular orientations as it travels through space, and this property is called polarization. There are different patterns that this polarization can take when mapped across the sky, and cosmologists have given them names borrowed from electromagnetism, calling them E modes and B modes to distinguish between patterns that have different mathematical symmetries, rather like the difference between the pattern of lines radiating outward from a point and the pattern of lines swirling around it. The E modes had already been detected by earlier experiments and were well understood to arise from the ordinary processes of sound waves and density fluctuations in the early universe, but B modes were more elusive and more tantalizing, because certain kinds of B mode patterns could only be generated by gravitational waves, by ripples in the fabric of spacetime itself propagating through the infant cosmos and gently twisting the polarization of light in ways that density fluctuations alone could never accomplish. On the 17th of March in the year 2014, the BICEP2 team held a press conference to announce their results, and the atmosphere in the room was one of barely contained excitement, though from this distance we may reflect on it with a gentler and more measured perspective. They reported that after careful analysis of their data, they had found a clear and statistically significant detection of B-mode polarization at a level that seemed to indicate the presence of primordial gravitational waves, and they quantified this detection using a number called the tensor-to-scalar ratio, which is a measure of the relative strength of gravitational wave fluctuations compared to ordinary density fluctuations, and the value they claimed was approximately R equals 0.20, which would have been a remarkably strong signal, far stronger than many theorists had expected or predicted. The announcement was reported widely and celebrated by many in the scientific community as a potential breakthrough of historic importance, and some senior figures in the field spoke in terms that suggested the discovery might warrant consideration for the highest honors in physics. But in the weeks and months that followed, a quieter and more cautious conversation began to unfold among researchers who were not part of the BICEP2 collaboration, and gradually the tone of that conversation shifted from excitement to concern. The central issue, which would eventually prove decisive, was the question of galactic dust, which is to say the tiny particles of matter that drift through our own Milky Way galaxy and which have their own faint glow at microwave frequencies, and this glow is itself polarized in ways that can produce patterns on the sky that might, under certain circumstances, be confused with the primordial signal that BICEP2 was designed to detect. The BICEP2 team had of course considered this possibility and had attempted to account for it in their analysis, but their estimates of the dust contribution relied in part on preliminary data and models that, as it turned out, may not have fully captured the complexity and strength of the dust emission in the particular region of sky they had observed. The European Space Agency's Planck satellite, which had been mapping the entire sky at microwave frequencies with extraordinary precision, began to release additional data in the months following the BICEP2 announcement, and this data painted a more complicated picture of the dusty foreground than had previously been available. By September of 2014, the Planck team had published an analysis suggesting that the level of dust polarization in the region observed by BICEP2 was higher than the BICEP2 team had assumed, high enough, in fact, that the entire claimed signal could potentially be explained as contamination from our own galaxy rather than as evidence of primordial gravitational waves from the dawn of time. This was not a conclusion reached in haste or with any sense of rivalry, but rather the careful and methodical working through of a difficult problem by researchers who understood that extraordinary claims require extraordinary evidence, and that the evidence must be examined from every angle before it can be accepted. In January of 2015, a joint analysis was published that brought together data from BICEP2, from a related experiment called the Keck array, and from the Planck satellite, and the conclusion of this combined effort was that once the dust contribution was properly accounted for, there was no significant detection of primordial gravitational waves remaining in the data. The signal that had seemed so clear and so exciting just months earlier had dissolved into the gentle glow of interstellar dust, and the tensor-to-scalar ratio was constrained to much lower values than had originally been claimed, values that were consistent with zero or at most with a very weak signal that would require far more sensitive measurements to confirm or rule out. It would be natural, perhaps, to view this episode as an embarrassment for the scientists involved, or as a cautionary tale about the dangers of premature announcements and press conferences, and there is certainly something to be learned from the sequence of events about the importance of patience and thoroughness in the evaluation of extraordinary claims. But there is another way to view what happened, which is to see it as an example of science working exactly as it is supposed to work, with results being announced, scrutinized, challenged, and ultimately corrected through the collective efforts of a community dedicated to understanding the truth rather than to defending any particular conclusion. The BICEP 2 team did not hide their data or dismiss the concerns of their critics, and the Planck team did not withhold their analysis or delay its publication. And in the end, the scientific community arrived at a more accurate understanding of the observations than any single group could have achieved on its own. And if this process was at times uncomfortable for those involved, it was also a demonstration of the self-correcting nature of empirical inquiry at its best. The search for primordial gravitational waves has continued in the years since, with new and more sensitive instruments being deployed to the South Pole and elsewhere, and the current upper limits on the tensor-to-scalar ratio have been pushed down to values less than approximately 0.06, which means that if primordial gravitational waves exist at all, they must be quite faint, fainter than many of the simpler inflationary models would have predicted, though still within the range allowed by more refined theoretical frameworks. The BICEP 3 telescope, which began observations in 2016, represents a significant improvement in sensitivity over its predecessor, and a larger project called the BICEP Array is now under construction, consisting of multiple telescopes working in concert to map the polarization of the cosmic microwave background with ever greater precision across a wider range of frequencies, which will allow for better separation of the primordial signal from the contaminating foregrounds of dust and other galactic emissions. The implications of an eventual detection of primordial gravitational waves, should one ever be achieved with confidence, would be profound in ways that are difficult to overstate while still maintaining the calm and measured tone appropriate to a bedtime narration. Such a detection would provide direct evidence that the universe underwent a period of exponential expansion in its earliest moments, confirming a central prediction of inflationary theory, and it would open a window onto physical processes that occurred at energy scales far beyond anything that can be probed by particle accelerators on Earth, scales at which the fundamental forces of nature may have been unified in ways we do not yet fully understand. The gravitational waves themselves would carry information about the quantum fluctuations that seeded the large-scale structure of the universe, the galaxies and clusters and voids that we observe today, and measuring their properties would tell us something about the specific mechanism that drove inflation and about the conditions that prevailed when the universe was younger than any other epoch we can directly observe. For now, the search continues, and the telescopes at the South Pole and elsewhere keep gathering photons that have been traveling for nearly 14 billion years, and the researchers keep refining their techniques for separating the faint whispers of the primordial universe from the louder but less interesting signals of our own galactic neighborhood. It is slow and painstaking work, conducted in one of the most challenging environments on Earth, and there is no guarantee that the signal they seek will ever be detected, for it may be that the tensor-to-scalar ratio is simply too small to measure with any foreseeable technology, or it may be that our understanding of inflation itself will need to be revised in light of what the experiments reveal. But this uncertainty is not cause for discouragement, for the value of the search lies not only in the answers it may provide but also in the questions it forces us to ask, and in the ever more refined picture of the universe that emerges from the effort to distinguish signal from noise, truth from artifact, the echoes of creation from the gentle glow of dust drifting between the stars. And so the work goes on, quietly and carefully, at the bottom of the world, where the air is cold and dry and the sky is dark and the microwave light of the ancient universe falls softly on the detectors of instruments built to measure disturbances in space-time that may have occurred before atoms existed, before light could travel freely through the cosmos, before anything that we would recognize as matter or energy had taken the forms we know today, and whether or not the primordial gravitational waves are ever found. The search itself is a testament to the patience and persistence of those who wish to understand how everything began, and that is a gentle and reassuring thought to carry with you as you drift toward sleep. And so we come now to consider what lies ahead, the quiet work that continues even as you settle into stillness, the ongoing effort to coax further secrets from this ancient light that has already told us so very much. The cosmic microwave background has been extraordinarily generous with its revelations, and yet there remain questions it has not fully answered, subtle signatures it may still contain, and so astronomers and physicists around the world are building new instruments, planning new missions, preparing to listen with ever greater sensitivity to this faint whisper from the dawn of time. High in the Atacama Desert of northern Chile, At an elevation of more than 5,000 meters above sea level, where the air is thin and dry and the nights are long and clear, a new observatory is taking shape on a site called Cerro Toco. This is the Simons Observatory, named for the foundation that has provided much of its funding, and it represents the next generation of ground-based cosmic microwave background observation. The Atacama is one of the driest places on Earth, which matters greatly for this kind of work, because water vapor in the atmosphere absorbs and emits microwaves, creating noise that can obscure the faint cosmic signal. At this altitude, above much of the atmosphere's moisture, the conditions approach those of space itself, and the ancient photons can reach the detectors with minimal interference from our planet's envelope of air. The Simons Observatory will deploy tens of thousands of superconducting detectors cooled to temperatures just a fraction of a degree above absolute zero, colder than the cosmic microwave background itself, colder than any natural environment anywhere in the universe. These detectors must be this cold because they work by sensing the tiny amount of heat deposited when a microwave photon strikes them, and if the detectors themselves were warmer than the radiation they are trying to measure, their own thermal noise would drown out the signal entirely. It is rather like trying to hear a whisper while standing next to a roaring furnace, and so the furnace must be silenced, the detectors chilled to a profound and unnatural cold, and only then can the whisper be heard. The observatory achieved its first light in the year 2024, which in the language of astronomy means it began collecting its first scientific data, turning its instruments toward the sky and recording the ancient glow for the first time. In the years ahead, it will map the cosmic microwave background with unprecedented precision, searching for patterns and features that previous instruments lacked the sensitivity to detect, building upon the legacy of the satellites that came before while pushing into new territory that only ground-based observatories with their larger collecting areas can explore. And yet the Simons Observatory is itself only a precursor to something larger still. The CMBS-4 project, where the S4 stands for Stage 4, represents an international collaboration of extraordinary ambition, a coordinated effort to deploy more than 500,000 individual detectors across multiple sites, both at the South Pole and in the Chilean Atacama. 500,000 detectors, each one a tiny superconducting sensor waiting in profound cold for the arrival of photons that have been traveling for nearly 14 billion years. The scale of this undertaking is difficult to fully appreciate, but it represents a commitment spanning many nations and many years, a collective decision that the remaining secrets of the cosmic microwave background are worth this sustained and substantial effort. The South Pole, despite its remoteness and the formidable challenges of working there, offers conditions that are in some ways even better than the Atacama for this particular science. The atmosphere above the pole is exceptionally dry and stable. The long polar night provides uninterrupted observing conditions for months at a time, and the elevation of the Antarctic plateau, while not as extreme as Cerro Toco, still places observers above much of the troublesome lower atmosphere. The South Pole Telescope has already contributed significantly to our understanding of the cosmic microwave background, and CMBS-4 will build upon this foundation, combining the complementary advantages of both hemispheres to achieve coverage and sensitivity that neither site could provide alone. Beyond these ground-based efforts, there are also plans for new space missions, instruments that would escape the atmosphere entirely and observe from the perfect quiet of orbit. The Japanese Space Agency has been developing a mission called LightBird, a small satellite designed specifically to search for the imprint of primordial gravitational waves in the polarization of the cosmic microwave background, those subtle curling patterns that would provide evidence of inflation in the universe's earliest moments. LightBird is expected to launch in the late years of this decade, and if it succeeds in detecting these patterns, or in placing stringent limits on their absence, it will tell us something profound about the physics of the Big Bang itself. NASA has also studied concepts for future space missions, including one called PICO, which would combine the advantages of space observation with a larger telescope and more detectors than any previous satellite. Whether PICO or something like it eventually flies remains to be seen, as these decisions depend on funding and priorities that shift over time, but the concepts exist, the technology is being developed, and the scientific community continues to advocate for these missions because the cosmic microwave background still has secrets to reveal. What might these future instruments tell us? What questions remain that the ancient light might answer? One concerns neutrinos, those ghostly particles that interact so weakly with ordinary matter that they pass through the Earth as if it were empty space. Neutrinos have mass, this we know, but how much mass they have remains uncertain, and the cosmic microwave background is sensitive to this question in subtle ways. Massive neutrinos affect how matter clumps together in the universe, leaving their fingerprints in the pattern of temperature fluctuations, and with sufficient precision in our measurements we may be able to weigh these elusive particles using the ancient light itself. There is also the question of how many species of relativistic particles existed in the early universe, particles that were moving at or near the speed of light and therefore contributed to the radiation content of the cosmos. We know of 3 types of neutrinos from particle physics experiments, but the cosmic microwave background provides an independent check on this number, and if it were to reveal evidence for additional species, this would be a discovery of the first importance, pointing toward new physics beyond our current understanding. So far the data are consistent with 3 neutrino species, but more precise measurements could either confirm this or reveal subtle deviations that would demand explanation. And there is the question of primordial non-Gaussianity, a technical term that describes a particular kind of statistical property in the pattern of fluctuations. If the fluctuations were generated by the simplest models of inflation, they should be very nearly Gaussian, which is to say they should follow a particular statistical distribution that is symmetric and well-behaved. But more complex models predict small deviations from this Gaussian pattern, and detecting such deviations, or ruling them out with confidence, would help us distinguish between different theories of what happened in the universe's first fraction of a second. The current limits on non-Gaussianity are already quite stringent, but future experiments may push these limits further, either finding the subtle deviations or confirming that the primordial fluctuations were as simple and Gaussian as the basic models predict. There is, however, a fundamental limit to what the cosmic microwave background can tell us, a boundary beyond which this particular form of light cannot see. The surface of last scattering, that moment 380,000 years after the Big Bang when the universe became transparent and the cosmic microwave background photons began their long journey, marks the edge of the visible universe as seen in light of any kind. Before that moment, the universe was opaque, filled with the fog of free electrons that scattered photons continuously, and no light from that earlier epoch has survived to reach us. The cosmic microwave background is, in a sense, a wall, the most distant surface we can photograph with electromagnetic radiation, and whatever happened before that surface remains hidden from our telescopes. But there may be other messengers from the earlier universe, particles that escape the primordial fog because they do not interact with electrons, particles that have been traveling freely since even earlier times. The cosmic neutrino background is one such possibility, a sea of neutrinos that decoupled from matter when the universe was only about 1 second old, long before the cosmic microwave background was released. These neutrinos are still present, filling all of space just as the microwave photons do, but they are extraordinarily difficult to detect because neutrinos interact so weakly with matter. Their energies are incredibly low, far lower than the neutrinos produced in nuclear reactors or by the sun, and current technology is not remotely capable of detecting them directly. Yet physicists dream of one day building detectors sensitive enough to capture these primordial neutrinos, to take a portrait of the universe from when it was 1 second old rather than 400,000 years old, to peer behind the curtain of the last scattering surface and glimpse the cosmos in its first heartbeats. This remains a distant frontier, perhaps decades or even centuries away, but the fact that these neutrinos exist, that they carry information about the earliest moments, provides a kind of hope that the universe has not forever hidden its origins from us. What the cosmic microwave background has already accomplished is nothing less than a transformation of cosmology itself, a change in the very nature of the field from one of rough estimates and competing theories to one of precision measurement and detailed consensus. When I was younger, cosmologists spoke of the Hubble constant being somewhere between 50 and 100 kilometers per second per megaparsec, a factor of 2 uncertainty that reflected the difficulty of measuring cosmic distances. They debated whether the universe was 10 billion or 20 billion years old, whether it was open or closed, whether it would expand forever or eventually collapse. The cosmic microwave background, combined with other observations, has replaced these debates with precise answers, not perfect answers, There are still uncertainties and tensions and questions, but answers good to the level of a few percent, answers that would have seemed miraculous to the cosmologists of earlier generations. We now speak of the age of the universe being 13.8 billion years, with an uncertainty of less than 1%. We know the geometry of space to be very nearly flat, the total density of matter and energy to be almost exactly the critical value that separates eternal expansion from eventual collapse. We know the proportions of ordinary matter, and dark energy with precision that improves with each new measurement. This is precision cosmology, the legacy of the cosmic microwave background and the instruments that have studied it, and it represents one of the great intellectual achievements of our species. And now, as you lie here in the quiet dark, consider this remarkable fact. The cosmic microwave background is not something distant, not something that exists only in the remote reaches of space between the galaxies. It is here, in this very room, passing through the walls, passing through you, filling every cubic centimeter of space with its ancient photons. There are approximately 400 photons of the cosmic microwave background in every cubic centimeter, which means that the volume of air you have just breathed in contains many billions of these primordial particles, each one carrying information from the universe's youth, each one having traveled for nearly 14 billion years to arrive at this precise moment and this precise location. You are immersed in the cosmic microwave background as a fish is immersed in water, and there is nowhere you could go, no place in all the universe, where you would not be bathed in this ancient glow. It is the most pervasive thing in existence, more numerous than all the atoms and all the stars, a gentle bath of radiation left over from a time before there were any stars at all. In a very real sense, the cosmic microwave background is humanity's most distant photograph, an image of the universe when it was young, a portrait of our cosmic origins. We do not often think of ourselves as having a birth portrait that is nearly 14 billion years old, but in a manner of speaking we do, and it hangs not in any frame but in the very fabric of space itself, visible in every direction we care to look, provided only that we have instruments sensitive enough to see it. It is the glow of our beginning, the light of our emergence, and it has been with us since before the Earth existed, since before the Sun ignited, since before the Milky Way gathered itself from the primordial gas. And it will remain with us as long as we endure, growing ever cooler, ever fainter, but never quite disappearing, a companion through all the ages to come, the soft persistent echo of the moment when everything began.